You stand in front of 3 boxes. One of them has $1 million inside. The other 2 are empty. A host tells you to pick one. You choose box A. Then, before opening it, the host opens box C and shows you it's empty. He asks if you want to switch to box B. Most people stick with their first choice. It feels like a 50-50 chance now. 2 boxes, 1 prize. But that instinct, it's wrong. And not just a little wrong. The math says you should always switch. Your odds jump from 1 in 3 to 2 in 3. I'd love to invite you to share in the comments where you're listening from and what time it is. It's incredible to think about how we're all connected through these stories and ideas. If you enjoy these thought-provoking explorations, consider subscribing to Tired Thinker so we can keep bringing you reflective narratives. Now, settle in, get comfortable, and let your imagination drift as we delve into the mind-boggling paradoxes and mysteries. But your gut tells you otherwise. That's the paradox. The 3-box paradox isn't just a puzzle. It's a mirror. It shows how humans handle probability, decisions, and uncertainty. You think you're being logical, but what you're really doing is trusting a feeling that doesn't line up with the facts. Let's break it down from the start. You're told to pick 1 box out of 3. That means there's a 1 in 3 chance you've picked the right one. The other 2 boxes together hold a 2 in 3 chance of having the prize. That much is clear. Then something strange happens. The host, who knows what's in the boxes, opens one of the 2 you didn't pick, and it's empty. Now he gives you a choice. Stick with your box or switch to the 1 remaining closed box. At this moment, it feels like the odds have reset. Like now it's 50-50. 2 choices, 1 win, 1 loss. That's how the brain frames it. But that's not how probability works. The key is in what the host knows. He didn't open a random box. He opened one that he knew was empty. That changes the game. It's not the same as flipping a coin. It's not a fresh start. It's a continuation of the original odds. Here's how it plays out. When you first pick, you have a 1 in 3 chance of being right. That never changes. 2 out of 3 times, your original choice is wrong. The host removes 1 wrong option from the other side. That doesn't make your first choice any better. It just concentrates the odds onto the box you didn't pick. If your first choice had a 1 in 3 chance, the remaining closed box now has a 2 in 3 chance. That's why switching works. Think of it this way. Imagine playing this game 300 times. You pick box A every time. The host opens an empty box every time. If you never switch, you'll win about 100 times. If you always switch, you'll win around 200 times. That's a massive difference. But knowing that still doesn't make it feel right. And that's the deeper part of the paradox. It's not just about math. It's about the tug of war between logic and emotion, between what we know and what we feel. This puzzle has been around for decades. It gained real attention when Marilyn Vos-Savant answered it in her column in the 1990s. She explained the math clearly. She said, "Always switch." But readers were furious. Letters poured in from PhDs and math teachers telling her she was wrong. They said it's 50-50. They called her stupid. But she wasn't. She was right. They were just too sure of their own thinking. This kind of thing happens outside of puzzles too. You make a choice. You get more information. But you stick with your first move because it feels safer. It feels like you've already invested in it. That's called commitment bias. And it shows up in all kinds of places: business, relationships, even war. Let's look at a different scenario. Imagine you're hiring someone. You pick a candidate out of a large pool. Later, you learn something concerning, maybe a bad reference. You also find a new applicant who looks stronger, but you've already made a mental commitment to the first one. You spent time on interviews. You told your team. Switching now feels like admitting you were wrong, so you stick with your first choice. And often, that's a mistake. The 3-box paradox teaches us to be less attached to initial decisions. It asks us to step back, to weigh the facts again once new information shows up. It's not just about boxes and money. It's about letting go of the need to be right. Back to the boxes. There's another layer that makes people uncomfortable: the idea that someone else knows more than you. The host's knowledge feels like cheating. It feels like the game is rigged. But it isn't. His knowledge is part of the setup. It's not an illusion. It's a filter. He shows you part of the truth, and it's up to you to make sense of it. People often ask, what if the host doesn't know what's in the boxes and just gets lucky? Then it's a different problem. In that case, the odds do shift to 50-50. But the original puzzle is clear. The host does know, and that makes all the difference. This is what makes the paradox so sticky. It's not hard math, it's just counterintuitive. It feels wrong even when you understand it. And that discomfort is what makes it useful, because the world is full of choices like this, where the obvious path isn't the best one. You'll find versions of this in casinos, in courtroom strategy, in software testing. Say you're debugging an app. You make an assumption early on about where the problem is. You spend hours chasing it, then new info shows up. A server log points somewhere else. But instead of switching focus, you stay locked on your original theory. You think, I've come this far, it has to be here. But that's the paradox. Your odds are better if you switch your focus. The problem isn't stupidity, it's pattern matching. Humans are good at seeing shapes in data, but sometimes those shapes are shadows. You think you see a fair fight between two boxes, but the real fight is between your comfort zone and your curiosity. There's a good reason we evolved this way. Sticking with a choice often saves energy, it reduces risk, it feels more certain. But in some systems, like probability games, those instincts backfire. Even when you explain this to someone, they might nod and still not switch. That's another aspect of the paradox. Knowledge doesn't always lead to action. People can understand something intellectually and still act against it. The mind is full of little traps like that. So maybe the three-box paradox isn't just about making one better choice. Maybe it's about noticing how we make choices in general. Noticing the moments we dig in when we should stay loose. Noticing the times we ignore what's in front of us because it doesn't match the story we already told ourselves. And if we can notice those moments, whether in games or life, we can start to shift. Not by force, not by trying to be perfectly rational, but just by pausing, looking again, and maybe sometimes choosing to switch. Imagine if what you do tomorrow could reach back and change what happened yesterday. Retrocausality isn't science fiction. It's a real idea in physics, strange, unsettling, and still very much under investigation. At first, it sounds like time travel, but it's not. It's more subtle than that. It suggests the future might have a say in shaping the past. Not in a dramatic movie-style way. No DeLoreans, no paradoxes, just a quiet tug backwards through time written into the equations. To get into retrocausality, you have to start with a problem. Quantum mechanics is full of them, but one stands out. Entanglement. Two particles, once linked, remain connected no matter how far apart they are. Measure one and the other knows instantly. It's as if the universe cheats to keep things in sync. Einstein hated this. He called it spooky action at a distance. He thought something must be missing, something hidden. Hidden variables, maybe. But decades of tests have ruled that out. Bell's theorem, tested again and again, shows the predictions of quantum mechanics are right. The weirdness isn't a bug, it's baked in. So physicists started looking elsewhere for explanations. And a few of them, just a few, asked a different question. What if the reason the particles are so perfectly linked is because the future measurement is sending information back to the past? This idea flips the usual direction of cause and effect. Normally, the cause comes first. A match lights, then the fire burns. You say something, and then the words leave your mouth. Time flows forward. But what if, in the quantum world, it doesn't always work that way? Take the delayed choice quantum eraser experiment. It sounds like a mouthful, but the setup is simple. You fire a photon, a particle of light, at a screen with two slits. The photon can go through either slit, or both. If you don't look, it acts like a wave and creates an interference pattern. But if you watch which slit it goes through, it acts like a particle, no interference. Now here's the twist. You can delay the decision to look or not look until after the photon has already hit the screen. And yet, your choice still seems to affect what the photon did, not what it does, what it did. As if your decision in the present reached back and rewrote the past. Some call this experiment a trick of interpretation, a sleight of hand with data. But others say it's real, that it shows time may not move in just one direction, that under certain conditions, the future can influence the past. This is retrocausality. It doesn't mean you can go back and kill your grandfather. That's the pop culture version. What it means is more like this. The rules that govern quantum particles might be time-symmetric. That is, the laws work just as well going forward as they do going backward. So the cause and effect chain isn't locked in one direction. It's a loop. The future can be part of the cause, not all of it, just part. That's hard to accept. It goes against almost everything we experience. Drop a glass and it shatters. You don't see shards pulling together and leaping back to your hand. But the deeper you go into physics, the more you find time symmetry hiding underneath. In classical physics, many equations don't care about time's direction. Newton's laws work the same way forward or backward. A ball rolls down a hill the same way it would roll up if you filmed it and played it in reverse. Entropy, disorder, only increases because of probabilities, not because the laws demand it. So even at that level, time isn't what we think. Quantum physics, though, takes this to another level, and that's where thinkers like Hugh Price step in. He's a philosopher of physics who argues that we've been too quick to assume time's arrow always points one way. He says maybe we see it that way because of how we live, bound to aging, to memory, to entropy, but that the universe itself might be indifferent. Here's an example. Imagine a game of pool. You strike the cue ball, it hits the 8 ball, which rolls into a pocket. That's cause and effect. But now imagine you only know the final positions, the balls at rest. Could you figure out how they got there? Sure, you could play the motion backward and get a scene that makes just as much sense. The physics allows it. Only your sense of time makes it weird. In some interpretations of quantum mechanics, like the transactional interpretation, this backward influence is built in. A particle sends a wave forward in time, and a second wave travels back from the future. The event happens only when those two waves meet and agree. It's not a popular model, but it works, and it doesn't require faster-than-light messaging or magical thinking. Still, most physicists avoid retrocausality, not because it's disproven, but because it's hard to work with. It makes us uncomfortable. It suggests that our actions are woven into a fabric that includes the future. That choice and chance might not be as free as we like to think. Say you flip a coin, it lands heads. You think the outcome was random. But what if, in some deep layer of the universe, that result was already written, both backward and forward? Not by fate, not by destiny, but by the structure of time itself, folding over in ways we can't see. This view opens a strange door. It means you're not just the product of your past, you're also, in a small but real way, shaped by your future. The things you haven't done yet may already be nudging you from behind. It doesn't hand you a script. It doesn't remove choice, but it complicates what we mean by before and after. Retrocausality stays on the edge of mainstream science for now. It's not ruled out, but it's not widely accepted either. Still, the experiments that keep brushing up against it don't go away, and every time they're repeated, cleaned up, refined, they leave behind a whisper. A suggestion that time may be more like a conversation than a march, a conversation where the present listens and the future speaks first. You look up, and there it is, the moon. But close your eyes, walk away, forget it's there. Does it still exist? That's not just a poetic question. It's one of the strangest problems in physics. Most people assume the moon is always out there. We take its presence for granted, like gravity or the air we breathe. But under the surface of that assumption lies a deeper, stranger possibility. The moon may not exist in the way we think it does, not when we're not looking. This idea doesn't come from science fiction. It came straight from the heart of quantum mechanics. In the early 20th century, physicists were forced to rethink reality itself. They discovered that, at the smallest level of nature, things only seem to be when we observe them. Particles exist in a blur of possibilities, different places, different paths, until someone or something measures them. The act of looking forces the universe to make a choice. So here's the unsettling twist. If observation determines existence, then what happens to something when no one is watching? Albert Einstein didn't like that question. He once asked, "Do you really believe the moon is not there when you are not looking at it?" He was frustrated. To him, the moon had to be there, whether anyone noticed or not. But the math behind quantum theory didn't back him up. It left room for doubt. At the quantum level, objects behave more like probabilities than things. A single electron doesn't sit in one place. It exists in a cloud of possible places, what physicists call a wave function. Only when we look does the wave function collapse into one location. It's like the electron makes up its mind only when it's being watched. Before that, it's undecided. It's everywhere and nowhere. Now this sounds bizarre, and it should, but it's been tested again and again. The double-slit experiment is one of the best-known examples. A single particle is fired at a screen with two slits. When no one checks which slit it goes through, the particle behaves like a wave, as if it went through both slits at once. But if a detector watches the particle, it behaves like a particle and only goes through one slit. The simple act of measuring changes the outcome. So what does that have to do with the moon? The moon is made of atoms. Atoms are made of particles. If particles don't have fixed positions until they're observed, what about the atoms that make up the moon? And if atoms behave this way, then what happens to a whole object made of billions of them? This is where quantum physics runs into the measurement problem. If small things need observation to exist in a fixed state, then at what point do things become real on their own? Is it size? Is it complexity? Or is it just that we're always watching large things, so they always seem to exist? Think about your phone. You leave it on the table and walk away. You assume it stays there. But if no one looks at it, and no camera records it, and no light reflects off it to be seen by anything, is it still there in a definite way? Most people would say yes. It's solid. It's physical. But quantum theory never quite confirmed that. It dodges the question. This leads to the idea of decoherence. That's what many physicists rely on to bridge the gap. When a particle interacts with its environment, light, air, anything, it becomes entangled with that world. Its blurry state becomes part of a wider system. This decoheres, locking it into a more stable form. So maybe the moon exists not because we look at it, but because it's constantly interacting with everything around it. Photons from the sun, gravity from the earth, the dust in space, maybe these keep it real even when we're not around. But even that doesn't give a full answer, because we're still not sure what counts as an observation. Does it need a conscious mind, or is any interaction enough? There's a famous thought experiment that plays with this idea, Schrödinger's cat. A cat is placed in a box with a quantum trigger that may or may not release poison. Until someone looks inside the box, the cat is both alive and dead. It's not a real situation, of course. It's a way to show how strange quantum rules get when applied to big things. Now take that idea and blow it up to the size of the moon. Is the moon both there and not there until something checks? It sounds crazy, but it follows the same logic. One way to explain this is with a metaphor. Imagine a room with a light switch. But instead of flipping the switch, the light only turns on when you open the door. Every time you check, the room is lit. But when the door is closed, you have no idea what's going on inside. In quantum terms, the room isn't just dark. It's in all possible states at once. It's only when you open the door that the system picks one. The moon may be like that room. Every time we look, it's there. It seems stable. But the act of checking may be what locks it into place. There's another layer to this: consciousness. Some theories suggest that the observer has to be aware, not just a machine or a sensor, that our mind plays a role in shaping the world around us. This view isn't mainstream, but it hasn't been ruled out. It opens doors to even weirder thoughts. If no one was ever conscious, would the universe exist at all? Now that doesn't mean the moon blinks in and out of reality like a light bulb, but it does mean we don't fully understand what it means for something to be. We've built rockets, gone to space, and walked on the moon's surface. But on the most basic level, we still don't know what happens to it when no one and nothing is looking. Imagine you wake up after a car crash and everything looks the same, but you remember dying. That's where quantum immortality begins. It's not a myth or a spiritual belief. It comes from a real theory in quantum physics called the many worlds interpretation. This interpretation says that every possible outcome of a quantum event happens in a separate branch of the universe. If you flip a coin, in one universe it lands heads, in another it lands tails. The universe splits. You don't notice, because your consciousness keeps following just one of those branches. Now imagine this idea stretched into something much bigger. Instead of a coin flip, it's a life or death situation. In some branches, you die. In others, you survive. If you are the observer in that event, you'd only ever continue in the version where you live. You'd never be conscious in the ones where you died. This is where the idea of quantum immortality takes shape. You always survive from your point of view. You may see others die, you may even suffer injuries, but your consciousness keeps threading through the timelines where you continue. From the outside, people may see your death, but from the inside, your own awareness, you never hit the end. That's not wishful thinking. It's a possibility born out of the math of quantum mechanics. Nobody built this idea to make people feel better. In fact, it's unsettling. It suggests that death isn't something you experience, just something other people see happen to you. Let's say you're in a lab experiment. You're in a sealed room with a machine that has a 50% chance to kill you instantly and a 50% chance to do nothing. You agree to the test. The switch flips. If the many worlds interpretation is correct, your consciousness will always wake up in the branch where the machine didn't kill you. Even if the test is repeated over and over again, from your point of view, you'll keep surviving. Others outside the room will see you die at some point, but you won't ever be aware of that version. To someone on the outside, this might look like you got incredibly lucky, surviving against all odds. But from your point of view, it's the only outcome that ever happens. You wake up again and again. You live through situations that should have killed you. And the more this happens, the more it feels like you're dodging something you can't even see. Of course, this isn't something we can test directly. You can't ask a dead version of yourself how it went. You only get access to the versions where you're still alive. And this is what makes the theory so slippery. There's no moment where you get to compare notes across timelines. You just keep waking up, assuming you made it. But if you've ever heard stories of people surviving things they shouldn't, falling out of planes, walking away from explosions, waking up after being declared dead, this theory gives a strange explanation. Maybe they didn't beat the odds. Maybe they're just following the thread of consciousness that always leads to survival. The other versions of them did die, but the part of them doing the observing never did. That doesn't mean you live forever in a healthy body. Quantum immortality only suggests that your conscious experience doesn't end. That could mean waking up paralyzed. That could mean slowly declining. In the most extreme cases, it could mean being trapped in a damaged brain that's still aware. So it's not a comforting idea. It doesn't promise peace. It promises persistence. Think of it like this. You're standing in front of a million doors. Behind one of them is death. Behind the others are hard lives, lucky escapes, near misses. Every time you open a door, the universe splits. In most of them, you die, but you can't follow those. You can only walk through the ones where you survive. So that's what you do, again and again. Maybe the path gets narrower. Maybe your body gets weaker, but the door keeps opening. It's also worth noting that this idea doesn't apply to people around you. You see them die, you grieve, you lose them. That's real. Their consciousness follows its own path. Yours just keeps going. That's one of the lonelier parts of the theory. Immortality isn't shared, it's isolated. You might outlive everyone. Not in a physical way, but in a perceptual one. The story never ends for you. This is where the philosophical weight starts to show. If you can never truly experience death, what does that say about your life? Does it make risk meaningless? Does it turn life into a maze of inescapable survival? Or does it just stretch the illusion of choice until it becomes unbearable? Some people hear about quantum immortality and feel invincible. Others feel trapped, because if death never comes, suffering might never end either. That might sound like a contradiction. How can you suffer if you're not alive in the versions where suffering should kill you? But again, the theory doesn't promise comfort. It just suggests continuity. You move forward in whatever version keeps you going. Even if your mind is damaged, even if your memories fade, as long as something behind your eyes can observe the world, that's the version you'll keep waking up in. And this leads to one of the most difficult parts of the theory. What happens if every branch becomes unbearable? What happens if every version left to you is one you wouldn't choose? Can your consciousness stop following the path? Or is it locked into the next door, no matter what's behind it? This is where most people stop talking about quantum immortality. Not because the science ends, but because the implications become too heavy. If survival is guaranteed, meaning becomes harder to define. If death never arrives, value becomes harder to place. But here's what you're left with: a theory that doesn't ask for your belief. It doesn't try to sell you peace. It just shows you what might be happening underneath your decisions, your close calls, your narrow escapes. You may already be walking through those doors without knowing it. Not as a miracle, not as a story, just as a consequence of how quantum systems unfold. It's a quiet idea, one that sits in the back of your mind. It doesn't need to be dramatic, it doesn't need to be proven, it just needs one thing to stay alive: the part of you that's still watching. Imagine if the past could change based on something you do right now. That's not a line from a science fiction movie. That's quantum mechanics, and it's very real. In the early days of physics, scientists believed that once something happened, it was done. Cause came first, effect followed. But experiments in quantum physics started to mess with that order. They showed that particles behave in ways that don't match what we expect in the world we see every day. One of the most famous examples of this is the double-slit experiment. But things got even weirder with what's called the delayed choice experiment. Start with a basic version. You shine a light, just a simple beam of light, at a wall with two slits. On the other side, there's a screen to catch the light that makes it through. If light behaves like particles, you'd expect to see two clusters, one behind each slit. If it behaves like waves, you'd get a pattern of bright and dark lines, an interference pattern, which happens when waves add up or cancel out. What you see on the screen tells you what light did on its way through. Did it act like a particle or a wave? Here's the strange part. When no one checks which slit the photon went through, the light acts like a wave and creates the interference pattern. But the moment you add a detector to see which slit it passes through, the interference disappears. Now it behaves like a particle. The photon picks a slit, goes through it, and hits the screen without interference. So the act of observing seems to change what the light does. This was already unsettling. It made scientists ask whether the photon somehow knows when it's being watched. But John Wheeler, a physicist with a taste for the bizarre, asked a deeper question. What if we choose to observe after the photon has already passed through the slits? That's the core of the delayed choice experiment. You set up the same experiment, but now you add a twist. The photon moves toward the two slits like before. But this time, you don't decide whether you'll detect which slit it goes through until after it's passed them. That's why it's called delayed choice. The photon has already gone through, or so it seems. And then you decide whether or not to look. What happens next shouldn't make sense. If you choose to detect the path, the photon acts like a particle, as if it went through one slit. If you choose not to detect, it acts like a wave and creates the interference pattern. But your choice comes after it should have already passed the slits. It's as if the photon waits to decide how to behave until you make your choice, even if that choice happens later. That seems to go against common sense. How can a decision made in the present affect what the photon did in the past? This isn't just a thought experiment. Scientists have built real versions of it. In one setup, a single photon is sent toward a beam splitter, which either reflects it or lets it pass. On the other side, two detectors wait. Depending on how the system is configured, after the photon has left the beam splitter, the detectors will show either interference, wave behavior, or no interference, particle behavior. The choice of configuration is made after the photon has already entered the system, and still, the results match the delayed choice. The photon's behavior seems to line up with what you choose to observe, even if you make that choice too late to influence anything directly. To make this even clearer, imagine a scenario. A single photon is traveling toward a fork in the road. It can go left or right. You don't build the rest of the path until after it's passed the fork. Sometimes you build it in a way that would show which path the photon took. Other times you build it so that the paths merge back together, erasing the which path information and allowing for interference. No matter what you choose, the photon acts like it knew what kind of setup you would finish. But how? There's no signal fast enough to tell it. No delay in the system, no way for the future to reach back into the past, at least not in the way classical physics would allow. One possible way to think about this is that the photon doesn't decide anything until it hits the final detector. From the photon's point of view, if it had one, everything between its emission and detection is part of one whole process. Maybe time doesn't flow the same way at the quantum level. Maybe it doesn't even exist the way we think it does. In the classical world, we imagine a clear sequence. First, this happens, then that. But quantum mechanics doesn't play by those rules. In these experiments, the outcome doesn't seem to be fixed until it's measured. And what you choose to measure defines what kind of history the photon appears to have had. It's as if the universe only decides what happened when you ask it a question. And the type of question you ask, particle or wave, changes what answer you get, and even what events appear to have taken place before you asked. That brings up the idea of wave function collapse. Before a measurement, a quantum object is described by a wave function, a set of all possible outcomes. It's not that the photon is either a wave or a particle, but that it's something undefined, something in between, until you force it to pick a side. And the delayed choice experiment seems to suggest that this collapse doesn't care about your idea of time. It happens when you interact with the system, not when the particle passes through a slit. This isn't just academic. Quantum mechanics underlies much of modern technology, lasers, semiconductors, MRI machines. But experiments like this show that we still don't fully understand the rules that run the show. Even after 100 years of testing and debate, quantum mechanics keeps surprising us. People sometimes say, well, maybe the photon took both paths, or neither, or something else entirely. But that's the point. We don't know what it was doing when we weren't looking. All we can say is what shows up when we do look, and how our choice of when and how to look seems to shape what we find. That makes the delayed choice experiment more than a scientific puzzle. It's a challenge to how we think about time, cause, and the nature of reality itself. Imagine flipping a coin and being told the chance of heads is -30%. It sounds like nonsense. In everyday life, probabilities range from 0 to 1. 0 means it won't happen. 1 means it definitely will. Anything between those two numbers is a shade of possibility. But below 0, that shouldn't even exist. Still, in quantum mechanics, there are situations where the math works out best when you allow probabilities to dip below 0. They call these negative probability states. To most people, this sounds like a broken idea. Probability is supposed to describe how likely something is. It's tied to how we bet, how we predict, how we understand risk. You can't have a minus chance of drawing a card from a deck or a negative chance that it will rain tomorrow. But in the quantum world, where the rules are different, the concept isn't as outlandish as it first seems. It doesn't mean that something impossible becomes likely, or that something strange will definitely happen. It's more a reflection of how certain measurements can't be pinned down without breaking the way we usually do statistics. Start with a classic example in quantum theory. Suppose you want to measure two things about a particle, like its position and its momentum. The Heisenberg uncertainty principle tells you that the more precisely you know one, the less you can know the other. In simple terms, if you nail down exactly where the particle is, you lose track of how fast or in what direction it's moving. And if you know its momentum precisely, you get fuzzy on where it is. This isn't because your tools aren't good enough. It's baked into the fabric of quantum mechanics. Because of that limitation, we can't just draw up a table like we would in classical physics. We can't make a full map of every possible position and momentum combination with regular probabilities. That's where something called a quasi-probability distribution comes in. It's like a probability distribution, but it bends the rules. One version of this is the Wigner function. The Wigner function can look like a regular probability map when applied to certain states. But in some regions, especially with quantum systems that have no clear classical counterpart, the function goes negative. Not everywhere, and not in every state, but enough to make you notice. These negative dips don't correspond to negative outcomes in the real world. You won't find a detector showing a -1 photon. Instead, it signals that the system is behaving in a way that defies classical logic. It's a flag that says, you're in quantum territory now. Let's put this into a more grounded example. Imagine you're trying to predict how a marble might roll across a table. In classical mechanics, you'd measure its speed and direction, maybe include a few details about friction, and you'd come up with a probability for where it will land. Now suppose your marble is actually a quantum particle. You try to make the same kind of prediction, but your math keeps throwing out tiny bits of negative probability in some regions. You don't see the marble land in negative space. You see it show up where the probabilities are positive. But the negative parts were necessary to balance the whole system. Without them, your predictions would fall apart. It helps to think of these negative values as part of an accounting trick. Not in the sense of cheating, but in the sense of keeping the math consistent with what the experiments show. You're not saying that something physically happened with a negative chance. You're saying the full picture. The wave function, the interference effects, the superpositions, all add up in a way that can't be explained with just regular positive probabilities. Some researchers compare this to a loan in financial terms. A bank balance can go negative, not because money ceased to exist, but because the total accounting needs to balance out. Likewise, in quantum theory, these negative values help explain how certain outcomes interfere and cancel each other out, like waves that collide and flatten. Interference is at the core of this. When two waves meet, they can add up to make a larger wave, or cancel each other to make a flat line. That's something we see all the time, like when soundproofing uses destructive interference to reduce noise. In quantum mechanics, the probabilities don't just add, they can subtract. And the math behind that sometimes shows up as negative probabilities. Another good place to see this is in quantum optics. When scientists study states of light, like squeezed states or entangled photons, they often map out their behavior using the Wigner function or similar tools. The presence of negative probability regions is a hallmark of true quantum behavior. If the whole map stays positive, that usually means the system could, in theory, be described by classical physics. When you see those dips below zero, you know you're dealing with a state that can't be explained by any classical means. This matters because it tells us where the boundary lies. It helps us test the difference between classical and quantum worlds. The Wigner function and its negative regions aren't just weird math, they're a sign that quantum rules are in play. They help researchers understand when a system crosses the line into true quantum territory. Let's return to a more intuitive picture. Picture two overlapping shadows. If the shadows line up, they get darker in some places. But if you shine light in just the right way, the shadows can cancel out. Some areas get lighter, not darker, because the overlapping shadows subtract instead of add. This isn't exactly how quantum mechanics works, but it's close in spirit. The negative probability states are like parts of the system that subtract instead of add. Not because anything's broken, but because that's how the system balances out. You might wonder why we bother with this idea at all. Why not just stick with regular probabilities and avoid the confusion? The answer is simple, because the world doesn't behave in a way that regular probabilities can always explain. Negative probability states show up in real experiments. They match the data. And when scientists try to describe certain quantum systems without them, they either get the wrong answers or run into contradictions. That's not to say everyone's happy with the term. Some physicists avoid it altogether. They say it's better to think in terms of mathematical tools than to try to stretch the meaning of probability. Others embrace it as a sign that quantum mechanics still has layers we don't fully understand. There's no suggestion here that negative probabilities will replace the standard ideas of probability in fields like statistics, gambling, or everyday decision-making. This is a special case, tied to the strange rules of quantum systems, but it shows that even the most basic ideas, like what a probability is, can bend when you look close enough. In quantum physics, what we think of as impossible often turns out to be a sign that we've reached the limits of our usual logic. Negative probability states are one of those signs. They don't point to new particles or new dimensions. They point to a gap between how we expect the world to work and how it actually does at its smallest scales. And in that gap, we find ideas that are hard to accept, but impossible to ignore. You sit in a chair. In front of you is a gun. It's wired to a quantum device, something like a radioactive atom that may or may not decay. If it decays, the gun fires. If it doesn't, the gun clicks harmlessly. The odds are 50-50. You press the button, and then nothing. You're alive. But here's the twist. You repeat the test again. Same setup, same odds. You press the button. Again, still alive. You go on. 10 times, 100, 1,000. Still nothing. How is that possible? This thought experiment is called quantum suicide. It takes an idea from quantum mechanics and pushes it to the edge. The question it explores is simple. If reality splits into multiple versions every time a quantum event happens, then what happens to you, your conscious experience, when your life is on the line? To get to that, we need to back up to a theory called the many worlds interpretation. In standard quantum mechanics, when a particle faces two possible outcomes, it's said to exist in a state of superposition. It's not in one state or the other, it's in both at the same time. But when someone measures it, they get a single result. It seems like the particle chooses one option and the other possibility disappears. Many worlds says that nothing disappears. Instead, the universe splits. Both outcomes happen, but in separate, parallel branches of the universe. You see one outcome, but there's another version of you in a different world who sees the other. It sounds strange, but it lines up with the math, and it avoids some of the weirdness around wave function collapse, the idea that observation causes change. In many worlds, nothing collapses. Every possible outcome plays out. There's no randomness, just branching. Now take that idea and apply it to life and death. Imagine a machine. It measures a quantum particle that has a 50-50 chance of decaying. If it decays, it triggers a mechanism that ends your life. If it doesn't, you stay alive. In many worlds, both results happen. There's a version of the universe where you die and one where you don't. But here's where the logic of the thought experiment takes a turn. You, the observer, only experience one version of events. You can't experience your own death. So from your point of view, your consciousness keeps flowing down the branch where you survive. No matter how many times you run the experiment, there's always some version of the universe where you live. And from your perspective, that's the one you're in. You become, in theory, unkillable, at least by random quantum chance. You're locked into the branch where you always make it. It's not a claim about immortality in the everyday sense. You still age, you can still die in other ways. But when your survival depends on a quantum event, and the many worlds interpretation is true, then the version of you who continues to exist is always the one who makes it through. This idea is uncomfortable. It takes the abstract nature of quantum theory and ties it to something very real, death. It shifts the conversation from particles and detectors to questions about identity, consciousness, and survival. And it pushes the limits of what science can say about the self. Let's walk through a version of the scenario. You're in a lab. You've agreed to test the machine. It's safe, there's no actual risk, but the device is set up to behave as if it could take your life. A particle has a 50% chance of decaying within the next second. If it decays, the machine sends a signal that would be lethal. If it doesn't, nothing happens. In your frame of reference, you press the button, you hear a click, then silence. You're fine. If the many worlds view is right, there's now a split. In one universe, the particle decayed. The machine did what it was built to do. You died. But you, the conscious, thinking, observing you, can't observe that version. In every case, you find yourself in the world where you survive. It's tempting to say this proves something. It doesn't. The thought experiment can't be tested in the usual way because it depends on subjective experience. You can't gather data from the branches where you don't exist. You can't confirm the other versions. It's a one-way door. That's part of what makes it a thought experiment and not a scientific trial. Still, it makes a point. It takes the rules of quantum mechanics and extends them into areas they're not usually applied. And it raises questions about how we define you. Are you a single thread of consciousness moving through a single timeline? Or are there countless versions of you, branching off every time something uncertain happens? Quantum suicide isn't about whether the gun goes off. It's about which version of reality you experience. If every possibility happens and your consciousness always follows the one where you live, then in some sense, you never stop. But that survival comes with a cost. In every branch where you don't make it, others watch you die. The version of you that lives doesn't see that, but it still happens. The theory doesn't save you from death. It just keeps some version of you alive in some timeline. You never see your own end, but that doesn't mean it didn't occur. It also leads to a darker idea sometimes called quantum immortality. The suggestion is that your consciousness will always continue to exist somewhere, always finding itself in a branch where it survives. But that's not the same as living well. That's not the same as being safe. In many branches, you might be hurt, trapped, or suffering. The one constant is that you're still conscious. That's not comforting. It's unsettling. There's also the issue of identity. If the universe splits each time a quantum event occurs, how do you define who you are? Are you the sum of your memories, your biology, a line of code running on a quantum path? And if there are countless versions of you, which one is the real one? Quantum suicide doesn't answer those questions, but it makes them harder to ignore. It's not meant to encourage anyone to test the idea. In fact, it's often presented to show the limits of how far we can take a theory. It exposes the gap between math and meaning, between what we can model and what we can live. What the experiment does best is force a kind of honesty. It removes the comfort of easy answers. It reminds us that if we really believe the many worlds interpretation, we have to take all its implications, even the strange ones. And it shows how quantum mechanics, for all its precision and power, still leaves us with mysteries at the center of our own awareness. Not just about the world around us, but about how we experience being part of it. You always know which way time flows forward. You drop a glass, it shatters, but you never see the pieces leap back into your hand. That's obvious. That's time's arrow. But here's the strange part. The laws of physics don't actually care which way time runs. They work just as well backward as they do forward. So why do we only experience time moving in one direction? The answer usually points to entropy. Entropy is a measure of disorder. A tidy room has low entropy. A messy one has high entropy. In physics, entropy tends to increase over time. That's the second law of thermodynamics. In a closed system, things move from order to disorder, not the other way around. That shift gives us a direction, an arrow for time. You can see it in everyday life. Ice cubes melt in a warm room, but water doesn't freeze itself into cubes without help. Heat flows from hot coffee into cooler air, not the reverse. Each of these is a change from low entropy to high entropy. That's why we say time moves forward, because we see entropy increasing. But this leads to a problem. The core equations that describe motion, Newton's laws, Maxwell's equations, even the Schrödinger equation in quantum mechanics, are time-symmetric. They don't include a preference for past or future. If you filmed two billiard balls colliding and played it backward, you wouldn't know which version was real. The math supports both. So where does the arrow of time come from? If the basic laws don't include it, why does entropy increase? One common answer is initial conditions. The universe began in a state of very low entropy. That's a simple starting point, but it's a bit like a trick answer. Instead of solving the mystery, it pushes it further back. Why did the universe start off so ordered? Why not a high entropy mess from the beginning? This is where things start to clash. Entropy says time moves from order to disorder, but the equations that govern particles don't care. They work forward and backward. That creates a tension between the arrow we see and the rules we use to describe what's happening. Imagine you have a closed box with gas molecules inside. Over time, they spread out evenly. That's entropy increasing. But if you could reverse every motion, every collision, every path, they'd come back together and pile up in a corner again. That would be entropy decreasing. The math allows it, but we never see it happen. Why not? One idea is that entropy increases because of probability. There are more ways for things to be disordered than ordered. A deck of cards shuffled once is more likely to be messy than sorted. It's not that it can't be ordered again, it's just very unlikely. That's the statistical view of entropy. But even this doesn't fully explain the arrow. It explains why high entropy is more common, but it doesn't explain why we don't see rare reversals in practice, at least not for large systems. Now, think about a thought experiment. Suppose you record a video of a cup falling and breaking. If you watch it in reverse, it's obvious something's off. That's because your brain tracks cause and effect. You know cups don't unbreak. But the physical process, reduced to particles and forces, is symmetrical. The visual oddness comes from your understanding of entropy and experience, not from the math. This brings up another issue. In quantum mechanics, time symmetry is even more baked in. The Schrödinger equation, which governs how quantum states evolve, is also time reversible. If you reverse the sign of time, the evolution still works. So where does entropy come from there? It seems to arise when you look at large systems, collections of many particles. When you start adding up the behavior of countless components, you get emergent properties. Entropy is one of those. It's not built into the microscopic rules. It comes out when you zoom out. But even so, it still feels like a patch. The math doesn't break time symmetry, but the real world does. So what gives? Then there's the problem of memory. You remember the past, not the future. That seems obvious, but it's deeply tied to entropy. Memory storage, whether it's a brain, a computer, or ink on paper, requires energy. It creates local increases in order, even as overall entropy goes up. You can only form a memory if there's a difference between one state and the next. That difference is only visible because entropy is increasing. You can't recall the future because it hasn't been written into the system yet. But again, that's an effect, not a cause. Now add in quantum measurement. In the Copenhagen view of quantum mechanics, particles exist in multiple states until measured. The wave function collapses when you observe it. That collapse looks like a one-way street. Before measurement, uncertainty. After a defined result. That feels like time is moving forward. But again, the equations before measurement don't prefer a direction. The asymmetry enters at the moment of observation, but only from our perspective. Whether this collapse is real or just an artifact of measurement is still debated. Another layer comes from cosmology. Some theories suggest that the universe's expansion creates an arrow of time. As space stretches, entropy increases. That makes sense in the context of a universe that began with the Big Bang, a hot, dense, low-entropy state that has been spreading out ever since. But the question remains, why was it low entropy to start with? That might not sound like a big deal, but it matters. Because if the arrow of time depends on how the universe began, then it's not a fundamental rule. It's a byproduct. And if that's true, then a universe with different starting conditions might not have a time arrow at all. Another way to think about this conflict is to flip a process. Take a simple example. 2 eggs scrambled together. You can't unscramble them. That's entropy. But if you had perfect information about every particle, every motion, every force, you could, in theory, reverse the process. It's just that the information needed is far beyond reach. That's the practical barrier. The theoretical one doesn't exist in the same way. So are we mistaking a practical limit for a fundamental one? This tension between entropy and time symmetry keeps showing up. In microscopic systems, time runs both ways. In large systems, entropy forces a direction. Some researchers try to explain this by decoherence, how quantum possibilities reduce to definite outcomes when they interact with the environment. Decoherence increases entropy. It creates a record of what happened. It's another path from reversible laws to irreversible experiences. But even decoherence doesn't pick a direction. It just reflects how the environment works. Once again, we're back to asking why our universe unfolds this way. And then there's the mirror image question. If entropy gives time a direction, what happens in a universe where entropy decreases? That kind of universe would look like ours in reverse. Order would increase. Broken things would mend themselves. People would grow younger. That may sound ridiculous, but from a physics standpoint, it's not forbidden. The math still works. It's just not what we see. So we live in a universe where entropy increases, and we've built our entire experience of time around that fact. But the rules underneath don't demand it. They allow for both directions equally. The arrow we follow isn't written into the laws. It's a product of how our universe started, how systems interact, and how information flows. Something strange happens when 2 tiny particles become linked. Change one and the other responds instantly. It doesn't matter how far apart they are. It could be a few inches, it could be across the solar system. The reaction is immediate. This is what Einstein once called spooky action at a distance. He didn't like it. He thought it meant something was missing from the theory. He believed in local realism, that what happens in one place shouldn't instantly affect something somewhere else. But experiments kept proving him wrong. This strange link is called entanglement. It happens when two or more particles become part of the same quantum system. They stop acting like separate objects. They start acting as one. If you measure one, the result will match the other in a way that can't be explained by coincidence. Here's how it works in practice. Imagine you have two photons. You generate them at the same time in such a way that their polarizations are connected. Polarization is just the direction the light wave vibrates, up and down, or side to side, or anything in between. When photons are entangled, their polarizations are locked together. If one is measured and found to be vertical, the other will always be horizontal. If one is diagonal, the other will match in a predictable opposite way. Now let's take those photons and send them in opposite directions. One goes to a lab in Paris, the other goes to Tokyo. They are now thousands of miles apart. But if someone in Paris measures their photon and sees that it's vertically polarized, the person in Tokyo will instantly know that their photon is horizontally polarized. The key word is instantly, not after a delay, not after a signal travels between the two. It happens faster than light can travel. According to Einstein's theory of relativity, nothing can go faster than light. So, if something on one side changes the other instantly, it can't be a normal signal. And that's what bothered Einstein. He argued that the particles must have hidden variables, some kind of internal instruction set that tells them how to behave ahead of time. In his view, the outcome was already decided when the particles were created. We just didn't know the values yet. This way, no spooky action would be needed. Everything would be local, no magic, no mystery. But then came John Bell. In the 1960s, physicist John Bell came up with a way to test whether these hidden variables were real. He built a mathematical framework that compared what you would expect to see if particles had preset instructions versus what you'd expect from quantum mechanics. This is now known as Bell's inequality. If the world works the way Einstein thought, the measurements would follow a certain pattern. But if quantum mechanics is right, the results would break that pattern. And they did. Over the next few decades, scientists ran many versions of the test. They set up pairs of entangled particles, measured them at different angles, and recorded the results. Each time, the results matched the predictions of quantum theory and violated Bell's inequality. That means the particles couldn't have been carrying hidden instructions. Something else was going on. To make things more airtight, they did what's called closing the loopholes. One experiment put the detectors so far apart that light couldn't travel between them fast enough to influence the result. Another used fast, random changes in the settings to rule out any prearranged communication. Even with these precautions, the entanglement held up. It became clear that measuring one particle really does affect the other, no matter the distance, no matter the timing. That doesn't mean we can use this for faster-than-light communication. Entanglement doesn't let you send a message across space instantly. That's because the outcome of each measurement is still random. You can't choose what result you get. You just know that when you measure both particles, the results will match in a way that follows the quantum rules. Here's a way to picture it. Think of two envelopes. You're told that one has a red card and the other a blue card. You shuffle them, seal them, and send one to Paris and one to Tokyo. When the person in Paris opens their envelope and sees a red card, they instantly know the one in Tokyo must be blue. There's no mystery in that. But in the case of entanglement, the colors aren't fixed in advance. The cards don't decide what color they'll be until one is opened. And somehow, when the first one is opened and turns red, the other instantly becomes blue, even if it's on the other side of the planet. That's the part that doesn't sit easily with our everyday view of the world. It's not that one particle is just revealing something it already knew. It's that the act of measuring one defines the state of the other. It's like reality doesn't settle into place until you interact with it. Now think about that. Two objects, far apart, yet acting like one. The outcome of a measurement in one place seems to shape what happens in another place, without delay, without any force we can see or measure. This raises questions about the nature of space itself. If particles can be so deeply connected across vast distances, maybe space isn't what we think it is. Maybe the distance between two things isn't a barrier at all, not at the quantum level. Entanglement also challenges the idea of separateness. In the quantum world, there's a kind of unity. Parts of a system don't always have their own identities. They share one. You can't fully describe one particle without including the other. That kind of thinking is hard to accept in classical physics, where everything has its own place, its own state, its own behavior. But quantum mechanics keeps showing us that the universe may be more deeply woven than we thought. People have tried to make sense of this in many ways. Some say the connection is not physical. It's just a sign that the math works differently at small scales. Others suggest that time and space are not the ultimate framework of reality, but just tools we use to describe what we see. Still others propose that all outcomes exist at once, in parallel versions of the universe, and what we experience is just one path among many. Whatever the case, entanglement forces us to rethink what it means for something to be real. If the properties of a particle don't exist until we measure them, then reality isn't fixed. It's shaped, in part, by how and when we look. That doesn't mean quantum physics is vague or untestable. The predictions are precise. The results are consistent. It's not chaos. It's a kind of order we don't yet fully understand. We're used to thinking that everything must have a cause we can trace. But in the quantum world, cause and effect are not always tied to space and time. Entanglement shows us that information, if that's what this is, can be linked in ways that break the rules of classical logic. Even now, we don't have a full explanation for how entanglement works. But we know it's real. We've tested it again and again, and each time, the universe gives the same answer. It's as if the particles are telling us, we're not separate. Measure one, and you change the whole. What if you could disappear from one place and reappear in another, without crossing the space in between? That sounds like fiction. But in quantum physics, something close to this already exists. It's called quantum teleportation, and it doesn't involve moving objects through space. Instead, it moves information, the kind that defines a particle's state. That state in the quantum world is everything. To understand what this means, think about a coin. You flip it, and it lands either heads or tails. Now imagine a quantum coin. Before you look at it, it isn't heads or tails. It's in a superposition, a mix of both. Once you observe it, it settles on one. This superposition is key to how quantum systems behave, and it's one of the reasons why teleportation without travel works at all. In the classical world, copying something is easy. You scan a document, you take a photo, you send a file. But in quantum mechanics, copying doesn't work the same way. There's something called the No-Cloning Theorem. It says you can't make an exact copy of an unknown quantum state. The act of measuring the state changes it. That's a problem if you want to move a quantum particle's state somewhere else. So scientists figured out a workaround. Instead of copying the state, you transfer it. But this transfer doesn't happen through regular travel. The particle itself doesn't go anywhere. Instead, the information that describes it gets destroyed in one place and rebuilt in another. That's the heart of quantum teleportation. Here's how it works. You start with two particles that are entangled. Entanglement is a quantum link that connects particles across space. If you measure one, you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance. He didn't like it, but experiment after experiment shows it's real. Now suppose you have a third particle, call it A. It holds the quantum state you want to teleport. You also have two entangled particles, B and C. Particle B is near A. Particle C is far away at the destination. You can't measure A directly because that would destroy its state. But you can do something else. You perform a special measurement on particles A and B together. This is called a Bell state measurement. When you do this, the state of A disappears. It's gone. But the measurement changes the entangled system. Particle C, the one far away, now holds the state that A used to have. It didn't travel. Nothing physical moved. But its quantum state, the full set of information about it, now exists in C. That's teleportation without travel. To make this clearer, imagine a locked box. Inside is a pattern you don't know. You can't open the box without destroying the pattern. But you want to send this pattern to someone far away. You prepare two identical boxes, entangled in a quantum way. One stays with you, the other goes to your friend. Then you do a certain action that links your box with the original. That action destroys your box's pattern. But your friend's box, far away, now has the same pattern inside. You didn't send the pattern through wires or waves, you didn't open the box, you didn't clone it, but now it's there. There's one important catch. For the process to work, you still need to send some classical information. After the Bell state measurement, you get a result. That result tells your friend what adjustment to make to their particle so it matches the original state. You send that result using a regular signal, one that travels at the speed of light. Until your friend gets that signal, they can't know exactly what state their particle is in. So quantum teleportation isn't instant communication. It doesn't let you break the speed of light. It doesn't let you send messages into the past. What it does is let you move a quantum state from one place to another without moving the particle itself and without copying it. Scientists have done this many times. They've teleported photons, the particles of light. They've also teleported atoms. The record distances keep growing. In 2017, researchers teleported photons from the ground to a satellite orbiting hundreds of kilometers above Earth. The method works, and it's getting more precise. This kind of teleportation isn't something you see with your eyes. There's no flash, no puff of smoke, no object vanishing and reappearing. What moves is information. And in the quantum world, information is power. The exact arrangement of spin, polarization, or phase, that's what defines a particle's behavior. If you can move that, you can recreate the particle's identity somewhere else. Now imagine the possibilities. Secure communication is one. If you can teleport quantum states, you can build systems that detect any eavesdropping. Because measuring a quantum system changes it, anyone trying to intercept would leave a trace. That's the idea behind quantum key distribution. But teleportation takes it further. It could allow you to send keys or information without actually transmitting the content itself. Another possibility is quantum computing. Quantum bits, qubits, are fragile. They can't be copied. They get disturbed by noise. But with teleportation, you can move qubit states around inside a quantum computer without disturbing them. That opens the door to more stable and scalable systems. You might not need wires or channels to connect every part. You just need entanglement. And while human teleportation is still fantasy, the ideas behind it are becoming clearer. Your body is made of atoms. Each atom has a quantum state. If you could somehow measure all those states, transmit the data, and recreate them somewhere else, you'd have a version of teleportation. But the challenges are enormous. You'd need to know the position and state of every atom. You'd need a receiver made of the same material, ready to be reshaped. You'd also need to destroy the original, because copying is not allowed. That's not something we can do now. Maybe not ever. But the basic concept, moving a state without moving the object, is already real. It happens in labs around the world, quietly, without flash, but with deep implications. So when people talk about teleportation, they usually think of science fiction. But quantum teleportation is not fiction. It's a process we can repeat, verify, and use. It doesn't break physics. It follows the rules, strange as they are. And those rules tell us something surprising. In the quantum world, the thing that matters most isn't what something is, but how it's described. And that description, the quantum state, can go from here to there without going through the space in between. You flip a coin, it lands on the table. You look down, it's heads. Simple, right? The coin was always going to be heads or tails. Your act of looking didn't change it. In the world we see around us, that's how things work. But in quantum mechanics, it's not so simple, and that's where the measurement problem begins. In quantum theory, particles like electrons or photons don't have a definite position or speed until they're measured. Instead, they exist in something called a superposition, a mix of all possible states. It's not just that we don't know the exact state, it's that the particle genuinely doesn't settle on a single state until we measure it. This creates a strange situation. Before measurement, a particle can be in multiple places at once, or spin in two directions at the same time. But the moment we measure it, we find only one result. The superposition collapses into one outcome. That sudden shift, the collapse, is where the trouble starts. Why does measurement change the system? What counts as a measurement? Does it require a conscious observer? Is the wave function real, or just a tool for predicting outcomes? These questions have no clear answers, even though the math works and the experiments match predictions. Imagine you're in a lab. You fire a single electron toward a screen. On the way, it passes through a barrier with two slits. If you don't place a detector near the slits, the electron behaves like a wave. It seems to go through both slits at once, and it creates an interference pattern on the screen, a series of light and dark bands. But if you place a detector at one of the slits to find out which path it takes, the interference disappears. The electron acts like a particle and goes through one slit. Just the act of measuring changes the outcome. So what exactly is this act of measuring? You didn't reach in and touch the electron. You didn't change the setup in any dramatic way. You just added a detector. That's what makes the measurement problem so hard to pin down. The presence of the measuring device alters the result, but how and why? The wave function is the mathematical tool that describes a quantum system. It gives you the probabilities of finding a particle in each possible state. Before measurement, the wave function spreads out, covering many possible outcomes. After measurement, it collapses to a single result. That collapse is not explained by the equations of quantum mechanics. It's added in as a separate step. No one knows what really causes it. One way to picture it is to think of a spinning coin again. But this time, it's not just spinning. It's in a strange state of heads and tails at once. Only when you look at it does it settle on one. In quantum theory, the coin isn't simply hiding its result. It literally doesn't have one until measured. This goes against everything classical physics teaches. In Newton's world, objects have properties whether or not anyone checks. A planet has a position. A ball has a speed. You can measure them more or less precisely, but they're always there. In quantum mechanics, those properties don't exist in a definite way until you interact with them. There have been many attempts to solve the measurement problem. One is the idea of hidden variables. Maybe particles do have set properties, but we just don't know them. This would restore a sense of order. Maybe the randomness we see is just a matter of incomplete knowledge. But experiments, including those testing Bell's inequalities, suggest that hidden variables can't fully explain quantum behavior, at least not in any local or simple way. Another approach is the many worlds interpretation. It says that all possible outcomes happen, but in different branches of the universe. When you measure a particle, the universe splits. In one version, you see it go left. In another, it goes right. Every possible result exists, but in a separate reality. This solves the measurement problem by removing the collapse. The wave function never breaks down, it just keeps evolving. But many worlds creates new problems. If all outcomes occur, why do we only experience one? Where are these other versions of reality? How can we test a theory that includes worlds we can't reach? There's also the idea of decoherence. In this view, the environment plays a key role. A quantum system is never truly isolated. When it interacts with its surroundings, air molecules, photons, even tiny vibrations, it loses its coherence. The superposition fades away, and the system appears to settle into a definite state. This matches what we see, but it doesn't explain why only one outcome becomes real. Decoherence describes how probabilities become very small for all but one result. It doesn't say why that one becomes the one we observe. Here's another scenario. Think about Schrödinger's cat. It's in a sealed box. Inside, there's a radioactive atom that may or may not decay. If it decays, it triggers a mechanism that kills the cat. If it doesn't, the cat stays alive. According to quantum mechanics, until you open the box and check, the atom is in a superposition, decayed and not decayed. That means the cat is also in a superposition, both dead and alive. But that's absurd. We never see half-dead cats. We only ever see one outcome. The measurement problem is about that absurdity. It's about the disconnect between the quantum world and the world we experience. We can describe quantum systems with incredible precision. We can predict the results of experiments with great accuracy, but we still don't know what the theory is telling us about reality. In the lab, this problem shows up again and again. You build a device to trap and manipulate a single ion. You cool it down to nearly absolute zero. You isolate it from all outside forces. You run a test. The results agree with quantum theory. But what did the ion do before you measured it? Was it in one state or in all possible states? Did your measurement bring the answer into existence? Some physicists take a practical view. They say quantum mechanics is a tool for making predictions. Don't worry about what's really happening. Just use the math, get the numbers, and move on. But that doesn't satisfy everyone. It feels like there's a gap between what we can calculate and what we can understand. This isn't just a debate in philosophy. It touches the heart of how we think about nature. It shapes the design of experiments and the future of quantum technologies. If we don't know what measurement really means, how can we be sure what quantum computers are doing or how to interpret the data they produce? The measurement problem keeps showing up, not because we're looking for it, but because we can't seem to escape it. Every time we try to understand quantum behavior in terms of ordinary cause and effect, it pushes back. It tells us that our assumptions may be wrong, that the world may not work the way we think it does. Quantum theory gives us power. It lets us build new tools and uncover new patterns. But at its core, it still asks a question we haven't answered. When does a possibility become real? What if just looking at something could change it? That sounds strange, even impossible. But in the quantum world, it's exactly what happens. In everyday life, observation doesn't change anything. If you look at a tree, it stays a tree. You don't influence its shape or its motion just by seeing it. But in quantum mechanics, the act of observing isn't passive. It plays an active role in shaping what happens. This is known as the observer paradox. At its core, this idea challenges how we understand measurement. In classical physics, a measurement tells you something that's already true. A thermometer tells you how hot it is. A scale tells you how heavy something is. These tools don't affect the thing they're measuring in any meaningful way. But quantum systems don't behave like that. In the quantum world, things exist in superpositions. That means a particle doesn't have one fixed state. Instead, it exists in a range of possible states at once. A photon can go through one slit, or the other, or both at the same time, until it's measured. That measurement doesn't just reveal what the photon was doing, it decides it. This is where the paradox begins. Measuring the system changes the system, not because the equipment interferes with it, but because of the way quantum mechanics works. You can't separate the act of observation from the outcome. The two are tied together. To understand how strange this is, imagine a coin spinning in the air. Until it lands, it's not heads or tails, it's both. That's just an analogy, of course. A real coin is always one or the other, even if you don't know which. But a quantum particle is different. Before measurement, it really is in both states at once. It's not just that we don't know which, it hasn't settled on one. Now picture this. A single electron exists in a cloud of probabilities. It might be here, or there, or somewhere in between. Its position isn't hidden, it's undefined. But when you observe it, say, by hitting it with a photon to find out where it is, it picks a location. Suddenly, the electron decides to be in one place. Your measurement causes the wave function to collapse. That's the term physicists use, wave function collapse. It means the electron's fuzzy, probabilistic nature snaps into a single, definite state. But the strange part is that this collapse only happens when a measurement is made. So what counts as a measurement? That question isn't easy to answer. Some say any interaction with the environment counts. Others say it takes a conscious observer. But most physicists agree on one thing. The system behaves differently depending on whether it's being measured or not. This idea played out clearly in the famous double-slit experiment. If you fire photons one at a time at two slits and don't measure which slit they go through, they create an interference pattern. That's wave behavior. It suggests each photon goes through both slits at once and interferes with itself. But when you set up a detector to watch which slit each photon goes through, the pattern changes. The interference disappears. The photons act like particles, choosing one slit or the other. The only difference is whether you're observing the path. It's not that the detector bumps the photon and knocks it off course. The change isn't physical in that way. It's about information. The moment you gain knowledge of the path, the wave-like behavior vanishes. The act of gaining information reshapes what the particle does. Now think about that for a second. The particle seems to know whether it's being watched, and it changes its behavior based on that, but there's no will involved. The particle doesn't think or decide, it simply responds to the setup. Yet somehow the presence or absence of observation changes the outcome. This leads to some odd scenarios. Suppose you set up an experiment where you can choose whether or not to observe the system, but you make that choice randomly, even after the particle has already entered the system. The results still depend on whether you end up observing. That creates a kind of tension between what's real and what's known. This is what makes the observer paradox so unsettling. It suggests that reality doesn't fully form until it's observed. That doesn't mean nothing exists when you're not looking, but it does raise the question, what is the state of something that hasn't been measured yet? Erwin Schrödinger illustrated this with a now famous thought experiment, the cat in the box. A cat is placed in a sealed box with a device triggered by a random quantum event, say the decay of a radioactive atom. If the atom decays, a poison is released and the cat dies. If it doesn't, the cat lives. According to quantum mechanics, until you open the box and check, the cat is both alive and dead at the same time. Of course, in real life, a cat isn't both. It's either alive or not. But the point of the example is to show how strange quantum logic becomes when scaled up. If observation causes collapse, then until the system is observed, it exists in a mixed state. So is the act of opening the box what determines the cat's fate? This might sound like philosophy, but it's grounded in real physics. In labs, physicists have put particles into superpositions and then measured how those superpositions collapse when observed. These effects have been seen not just in photons and electrons, but in molecules made up of hundreds of atoms. And every time, the outcome depends on whether and how a measurement is made. Not when you think something should have happened, but when you actually check. Another way to see the paradox is to think in terms of questions. A quantum system doesn't answer a question until you ask it. And once you do, the answer becomes part of the system's history. Before that, there's no definite answer, just probabilities. But asking the question changes everything. So the paradox lies in this: the observer shapes what is observed, not because of faulty equipment or limited knowledge, but because that's how the quantum world works. It resists separation between subject and object, between the one looking and the thing being looked at. That doesn't mean we control reality with our minds. That idea often shows up in pop science, but it's a misunderstanding. The paradox isn't about belief, it's about interaction. It shows that at the smallest scales, knowing something and causing it are often the same thing. The observer paradox isn't just about one strange experiment. It's a feature of the whole quantum framework. Whether it's spin, position, momentum, or polarization, the same pattern shows up. Unmeasured systems behave one way, measured systems behave another. And the difference isn't subtle, it defines what happens. This leaves us with a question that doesn't have a clear answer. What is reality when no one is looking? In the classical world, that's easy. A rock is still a rock. But in the quantum world, things don't take shape until they're pinned down. That act of pinning, of observing, changes the game. Two particles, one system. No matter how far apart they are, a change to one instantly shows up in the other. That's quantum entanglement. It doesn't behave like anything we see in the everyday world. To understand this, think about flipping a coin. You flip one and it lands heads. You flip another, it lands tails. The results are random and independent. That's how we expect nature to work. Separate things act on their own. But entangled particles don't follow that rule. You measure one, and the other responds instantly, even if it's on the other side of the world. It starts when two particles interact in just the right way. That interaction links their properties, like their spin or polarization. After that, their states are not separate anymore. They're described by a single wave function. That means you can't talk about one without also talking about the other. They've become one system, even if they're moving in opposite directions at the speed of light. Let's say you create a pair of entangled electrons. You know that when you measure one, it will either spin up or spin down. But here's the trick. You don't know which until you measure it. And until that moment, it's not that each electron has a hidden value waiting to be revealed. Instead, both are in a superposition. That means they don't have a fixed state yet. Only the relationship is fixed. If one is spin up, the other must be spin down. Imagine you send one of the electrons to a lab in New York and the other to a lab in Tokyo. The moment the New York lab measures its particle and sees spin up, the Tokyo lab knows, without even checking, that their particle will be spin down, and they don't have to wait for a signal. It doesn't matter how far apart the particles are. The connection shows up instantly. Einstein didn't like that. He called it spooky action at a distance. He thought there had to be some hidden variables, something unknown but local, that determined the outcome. In his view, the particles must have carried some kind of instructions from the start. They knew what result to give when they were measured. That would save the idea of local realism, the belief that things have properties before we look, and that signals can't travel faster than light. But then came John Bell. Bell asked a simple question. What kind of results would you expect if Einstein's view was right? He wrote an inequality, a kind of limit, that showed what should happen if hidden variables were real. Then he said, test it. Physicists ran those tests again and again. They used photons, electrons, ions, and every time they found the same result. The inequality didn't hold. The results matched quantum theory, not local realism. That meant either information traveled faster than light, or the particles didn't have set properties before being measured. Now, this doesn't mean you can use entanglement to send messages instantly. You can't control what result you'll get when you measure your particle. The outcomes are still random. It's only when you compare results after the fact that the connection shows up. But the link is real, and it's not just a trick of statistics. Think of it like this. You and a friend each get a sealed envelope. Inside is either a red card or a blue card. You know the cards were packed so that one is red and one is blue, but you don't know which is which. You go to opposite ends of the city. You open yours and see red. That means your friend has blue. It feels like a simple case of shared information. But in the quantum version, the cards don't have colors until you open the envelope. And the color you find isn't random by itself. It's only random in combination with your friend's result. The moment you look, the other envelope gets defined too, even if no one opens it for hours. The two results are tied together from the start, but not in a way that makes sense under regular rules. In some experiments, physicists have moved the detectors miles apart and made the choice of measurement randomly, just before the particle arrived. Still, the results showed entanglement. That ruled out the idea that some signal could sneak ahead and set the outcome. There wasn't time. It gets stranger. The choice of what to measure, say the angle of polarization, can be made after the particle is in flight. And still, the measurements come out correlated. It's like the universe doesn't care about the timing. The entangled system knows what to do, no matter when or where you decide to check it. This brings us back to the idea of the wave function. In quantum mechanics, particles are described not by fixed traits, but by a set of probabilities. Only when you measure them does the wave function collapse into a definite result. And in the case of entanglement, the wave function includes both particles at once. It's one equation, one state, for two things. Until you interact with one part of the system, the full picture is still in play. In some versions of quantum theory, this isn't a collapse at all. The many worlds view, for example, says that all possible outcomes happen, but in separate branches of the universe. When you measure your particle and get spin up, the universe splits. In another branch, you see spin down. Your partner's particle does the same. The link is preserved just across different branches. But even that doesn't remove the weirdness. It just shifts it. Entanglement isn't just a curiosity. It plays a role in real-world technology. Quantum cryptography uses it to make secure keys. If someone tries to intercept the particles, the entanglement breaks down. That alerts the users that the line isn't safe. Quantum computers aim to use entangled particles, qubits, to perform calculations that regular computers can't handle. In both cases, the strange properties of entanglement become tools, not just theories. Still, no one has a full answer to what's really going on beneath the math. The equations work. The predictions match the data. But what this says about the nature of reality, about cause and effect, time, space, that's still up for debate. You can separate the particles by light years, you can run the experiment again and again, but every time you measure one, the other falls into place like it always knew what was coming. The link remains. Quiet, instant, and impossible to ignore. Imagine holding a coin above your hand, flipping it into the air and catching it without looking. Until you lift your hand and check, you don't know if it landed on heads or tails. But deep down, you still believe it's one or the other. You just don't know which yet. In the quantum world, that's not how things work. Until you look, the coin isn't heads or tails. It's both. That's the heart of superposition, and it's one of the strangest ideas in quantum mechanics. Superposition means that a quantum system doesn't have to pick a state right away. Instead, it can be in a mix of all possible states at once. Not switching back and forth, and not undecided, actually in all the states at the same time. Only when you measure it does it choose one outcome. This idea goes back to experiments with electrons, photons, and other small particles. A simple example is the double-slit experiment. When a single electron is fired at a barrier with two slits, and you don't try to detect which slit it goes through, it forms an interference pattern on a screen behind the barrier. That pattern shows wave behavior. But here's the strange part. The electron seems to interfere with itself. It behaves as if it passed through both slits at once. That's superposition. In classical physics, this can't happen. A baseball thrown at a wall with two holes can only go through one. But electrons and photons don't follow classical logic. They exist in a superposition of going through slit A and slit B until you observe them. When you try to find out which slit the particle went through, the superposition breaks. The particle behaves like it went through one slit, and the interference pattern disappears. It's as if the act of measuring collapses the system from many possibilities into one. The paradox arises because this doesn't just apply to electrons. In theory, it should apply to anything, no matter the size. That's where Schrödinger's cat comes in. Erwin Schrödinger came up with a thought experiment to show how strange superposition gets when scaled up. You take a sealed box. Inside is a cat, a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The setup is simple. If the atom decays, the Geiger counter triggers the hammer to smash the vial and release the poison, which kills the cat. If the atom doesn't decay, nothing happens, and the cat stays alive. Quantum mechanics says the atom is in a superposition of decayed and not decayed until you measure it. So the cat, tied to that outcome, is also in a superposition, both dead and alive at the same time. That seems absurd. In the real world, cats are either alive or dead, not both. But if you take the math seriously, and if quantum rules apply to everything, then superposition doesn't stop at tiny particles. It should apply to large systems, even living things. That's the paradox. We don't see dead and alive cats. We see one outcome. So something must change between the quantum world and the everyday world we experience. But where does that change happen? Is it during measurement? Is it when something becomes large enough? Or is it tied to the presence of an observer? No one has a definite answer, which is why this is still debated. Some physicists suggest that superposition collapses when a quantum system interacts with its environment. This idea is called decoherence. The system gets entangled with everything around it, air, light, atoms, and its delicate state breaks down. It no longer shows interference, and it looks like it has picked one outcome. But decoherence doesn't explain why only one result shows up. It just explains why we can't see the superposition anymore. Others suggest that all possible outcomes actually happen in separate, parallel worlds. This is called the many worlds interpretation. In the cat example, one world has a dead cat and another has a live one. Both are real, but we only see one because we follow one path through the branching structure of possibilities. That removes the need for a collapse, but it raises a different question. If all outcomes exist, what does it mean to observe anything? Superposition itself isn't hard to see in action. Scientists have trapped atoms and cooled them down to near absolute zero. In that quiet state, they've watched atoms enter superpositions, spinning clockwise and counterclockwise at the same time, for example. In labs, photons have been placed in superpositions of multiple paths. Even small mechanical devices, visible under a microscope, have have been coaxed into superposition states, vibrating and not vibrating at once. But all of this is done in tightly controlled environments. The moment these systems interact with something outside, like air molecules or heat, they lose the superposition. The effect is fragile. That's why we don't see superposition in our daily lives. Everything around us constantly interacts with everything else, collapsing those states before we ever notice them. To understand how strange this is, imagine trying to use superposition in a decision-making process. Say you're flipping a quantum coin, something like a qubit, the basic unit of quantum information. A qubit can be in a superposition of 0 and 1. It's not a 50-50 guess like a regular coin. It's genuinely both at once. But when you measure it, you only get one outcome. So if you're using this to make a choice, you're not dealing with randomness in the usual sense. You're dealing with a system that holds every outcome inside itself until the last moment. This is what makes quantum computing so different from classical computing. Classical bits are either on or off, 0 or 1. Qubits can be in a superposition of both. That means they can, in theory, process many possibilities at once. But the challenge is keeping them in superposition long enough to use that power. Interference, noise, and decoherence can all collapse the state too early. That's why building a stable quantum computer is so hard. Think of it like this. Imagine trying to write a novel where every sentence is both written and unwritten until you open the book. The moment you read it, only one version becomes real. But before that, all possible stories sit inside, layered together. That's the strange landscape superposition offers. It's not about uncertainty or lack of knowledge. It's about the system genuinely being in all allowed states at once until an interaction forces a choice. The paradox comes from trying to fit that idea into a world where we expect things to be one way or the other. A cat can't be both dead and alive, but a quantum system can. And that means we have to rethink what reality means at the most basic level. Are particles really in definite states when we're not looking? Or does the world take shape only when we interact with it? Even now, we don't fully know. You flip a coin. It spins in the air. While it's spinning, it's not heads or tails yet. It has the potential to land either way. But once it hits your hand and you look at it, it's one or the other. That's a simple analogy. But in quantum mechanics, something much stranger is going on. In the quantum world, things don't exist in just one state until they're measured. A particle like an electron doesn't have a definite position or speed until something forces it to settle on one. Instead, it exists in a range of possibilities. We describe that range using something called a wave function. The wave function is a mathematical tool. It tells you the chances of finding a particle in different places or states. It's not a physical wave, like water in a pond, but it acts like one in the equations. Where the wave is high, the chance of finding the particle there is high. Where the wave is low, the chance is low. But until you actually look, until you measure, the particle isn't in any one spot. It's spread out across all the places where the wave function has value. When you measure, something changes. The wave function, which was smooth and spread out, suddenly becomes sharp and narrow. The particle appears in one place, not many. That sudden jump is what we call the collapse of the wave function. Let's try another way to picture it. Imagine you're baking cookies. You make a dozen, and you put them all in the oven. But here's the twist. The oven has a strange rule. Until you open the door and look inside, every cookie is in every possible shape it could take. Star, heart, circle, square. Not just randomly, but all at once. As far as you know, each one is every shape at the same time. But the moment you open the oven, the cookies snap into just one shape each. That's what collapse looks like in the quantum world. Before you observe, the system holds all the possibilities. The moment you observe, it picks one. But this isn't just about cookies or metaphors. This is about the nature of reality. If a particle doesn't have a defined position until we look, what does that say about the world when no one is looking? Is it real? Is it still there in a definite state? Or is reality only shaped when we interact with it? Physicists like Niels Bohr believed that measurement plays a special role. According to the Copenhagen interpretation, which Bohr helped shape, the wave function is not a description of the particle itself, but of what we can know about the particle. The collapse happens when information is gained, when an observation turns a possibility into a fact. Other scientists disagreed. Some said the collapse isn't real at all. They argued that the wave function never collapses. It only looks that way because we become entangled with the particle. In this view, called the many worlds interpretation, every possible outcome happens, but in different branches of the universe. When you see the cookie as a star, there's still another version of you in another world who sees a heart. But let's stay with the basic idea. One world, one outcome. A particle is in many states until measured. When measured, the wave function collapses to just one. What makes that collapse happen? That's the puzzle. You might say, well, it's the measuring device. But what counts as a measuring device? Does it need to be a machine? Does it need to involve a person? Could it be any interaction that pulls the particle into contact with the environment? Some experiments suggest that measurement doesn't have to involve a conscious observer. It can be as simple as a detector clicking or an atom absorbing a photon. But the result is the same. The wave function stops being spread out and locks in a result. To see how strange this gets, imagine firing one electron at a time at a barrier with two slits, like in the double slit experiment. If you don't measure which slit the electron goes through, it creates an interference pattern, like it went through both slits. If you add a detector to see which slit it uses, the pattern disappears. Now the electron acts like it picked just one path. Measuring which path it took forces the wave function to collapse. It stops being a spread-out wave and becomes a point-like particle with a history. But the collapse doesn't happen gradually. It's instant. One moment, the wave function stretches across space. The next, it snaps into a single spot. This goes against how most things in nature behave. Waves on a pond don't suddenly stop being waves when you look at them. But quantum waves do. This instant collapse creates other problems. Say a particle is in a superposition, a state where it's in two places at once, according to the wave function. These places could be miles apart. When you measure the particle and find it in one place, the wave function collapses everywhere else too. Instantly. Even in places light couldn't reach in that time. Einstein didn't like that. He called it spooky action at a distance. It seemed to break the rule that nothing can travel faster than light. But experiments showed that nature doesn't seem to mind. The collapse happens and there's no signal to track. It just is. This raises a deeper question. Is the wave function real, or is it just a tool we use to guess the odds? Some physicists say the wave function is just information, a way to describe what we know or don't know. In this view, collapse isn't something that happens in the world, it's something that happens in our minds. The moment we gain new knowledge, our description updates. Others argue that the wave function is as real as anything else, and its collapse reflects something physical. But if that's true, we still don't know what causes it or how it fits into space and time. To add more to this, think about Schrödinger's cat. It's a famous thought experiment that puts the problem of collapse into a box. Inside the box is a cat, a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, the poison is released, and the cat dies. If the atom doesn't decay, nothing happens, and the cat lives. But according to quantum mechanics, until someone opens the box and checks, the atom is both decayed and not decayed. The cat is both alive and dead. Only when you open the box and observe does the wave function collapse, and the cat becomes definitely alive or dead. People often ask, is the cat really both alive and dead, or is that just a problem with how we describe things? The collapse of the wave function turns that question into something we can't avoid. It sits at the heart of what makes quantum mechanics so different from classical physics. In the world we know, things have definite properties, whether we look or not. In the quantum world, those properties may not even exist until we check. There's still no agreement on what the collapse really means. Some think it's a shift in knowledge. Others say it reflects a deeper reality we haven't fully grasped. Some want to avoid collapse altogether and look for other ways to explain the results we see in experiments. But no matter how we frame it, the idea of the wave function and its sudden collapse forces us to rethink what we mean by measurement, by observation, and by reality itself. It's not a trick or illusion. It's part of how the quantum world works, and we're still trying to understand what that means. What if two people saw the same event and disagreed on whether it even happened? Not because they remembered it differently, but because physics gave them different realities. That's the question at the heart of Wigner's friend. Start with the basics. In quantum mechanics, measurement changes things. Before a system is measured, it exists in a superposition, a mix of possible states. But once it's measured, the wave function collapses. The system settles into a definite state. This isn't controversial inside quantum theory. It's what the math says. But Eugene Wigner asked something most people didn't. What happens if the measurement itself is observed by someone else? Picture this. There's a lab, completely sealed from the outside world. Inside is Wigner's friend. She performs a classic quantum experiment, say, measuring the spin of a single electron. Before she looks, the electron is in a superposition, both spin up and spin down at once. Once she measures it, she sees one result. Maybe she sees spin up. From her point of view, the wave function has collapsed. The result is real. She writes it down. She knows what happened. But Wigner, standing outside the lab, hasn't opened the door yet. He doesn't know what she saw. From his perspective, the lab, including his friend and the electron, is still part of a larger quantum system. As long as he doesn't interact with it, he can describe the entire lab using a wave function. That wave function includes both possibilities, that his friend saw spin up and that she saw spin down. In a sense, he treats her like a quantum object. So here's the issue. Inside the lab, Wigner's friend has a definite outcome. Outside the lab, Wigner treats the whole setup as being in superposition. He says no collapse has occurred. Both outcomes still exist in some form. That creates a tension. Two observers looking at the same experiment have two completely different views of reality. One says the result is fixed, the other says it's still undecided. This isn't about belief or misunderstanding. The math allows both perspectives. The problem is they can't both be right. Either the wave function collapses when the friend measures it, or it doesn't collapse until Wigner observes the lab. But which one is true? You might try to solve this by saying, well, collapse happens when a conscious observer sees the result. That was Wigner's original idea. He thought consciousness played a special role. But that brings in new questions. What counts as conscious? Is a camera not enough? What about a computer? Let's take a more grounded view. Imagine a modern version. A lab uses an automated machine to measure a quantum system. The result is recorded on a screen. A technician reads it. Then, an outside observer, unaware of the result, models the entire lab, including the technician, as a quantum object. That's Wigner's friend brought into real technology. Does the machine cause collapse, the technician, or does the system stay in superposition until someone else checks? This isn't just philosophy. In 2019, a group of researchers tested a version of the Wigner's friend setup. They used entangled photons and measured them in ways that mimic the nested observation structure. The results were unsettling. They suggested that different observers could, in principle, record inconsistent results that are still mathematically valid. That hints at something deeper. Quantum theory might not be describing one objective reality that everyone shares. Instead, it may describe a set of experiences, each tied to a specific observer or frame. In other words, reality could be relative, not in the way Einstein meant with motion and speed, but in terms of facts themselves. To make it more concrete, imagine this. Alice is inside a lab. She measures a particle and sees that it's spin down. She calls it out, writes it down, logs it into a system. To her, it's a fact. Bob, standing outside the lab, hasn't looked yet. He sets up an interference experiment designed to test whether the lab is still in a superposition. He runs the numbers and finds that yes, the lab, including Alice, is still in a mixed state. His interference pattern shows no collapse. So Alice and Bob have two different accounts. One has a definite past, the other has probabilities, and yet both are consistent with the theory. Now here's the problem. If Bob can measure interference, it suggests no collapse happened. But if Alice has recorded a definite result, collapse must have happened. These two can't be true at the same time, in the same universe, without contradiction. One way out is to say collapse is not a physical process, just a tool we use to update our knowledge. That's what some interpretations suggest, like the many worlds view. In that case, both outcomes happen in separate branches of the universe. Alice sees spin down in one world, spin up in another. Bob's superposition reflects all branches, and nothing ever collapses. But that brings new questions. What defines a branch? When do the worlds split? And if they're real, why can't we ever see the others? Another way is to say facts are not global. Alice's outcome is real for her. Bob's interference is real for him. There is no shared reality that covers both. That's the idea behind relational quantum mechanics. It says all properties are relative to the observer. Still, that breaks with how we usually think of science. We assume there's a single world, and we can all compare notes. If two people disagree about an experiment, they can go back, check their instruments, and sort it out. But in the Wigner's friend setup, the disagreement isn't due to error. It's built into the structure. Some physicists argue that this means quantum theory is incomplete. Maybe we need a deeper theory that resolves these paradoxes. Others say the problem lies in how we think about measurement. Maybe we need to rethink what it means to observe something at all. In everyday life, none of this shows up. When you flip a coin, it lands heads or tails. You don't worry about whether someone outside the room thinks it's still spinning. But quantum systems don't behave like coins. They don't settle until observed. And even then, who counts as an observer can change the outcome. Wigner's friend pushes this to the limit. It asks us to think about what we mean when we say something happened. Is a fact still a fact if someone else can model it as a possibility? Can two truths exist side by side without either being wrong? These are not easy questions, but they're not avoidable either. They strike at the foundation of what physics is supposed to do. Describe the world in a consistent way. When two observers can't agree on what is real, that's not just a detail, it's a crisis in the basic story science tells about reality. You drop a glass on the floor. It shatters into pieces, but you never see the pieces jump back up and form the glass again. Time moves in one direction. At least, that's how it feels. But if you ask the equations of physics, they say something else. They say time could go forward or backward. The rules would still work either way. That's what we call time symmetry. This is where the paradox begins. The fundamental laws of physics, the ones that describe how particles move, don't care about the direction of time. They work just as well in reverse. Take Newton's laws, Maxwell's equations, even the Schrödinger equation in quantum mechanics. Flip time and the math holds up. You could rewind the universe like a tape and nothing in the equations would complain. But reality doesn't play along. We only ever experience one direction, forward. We age. We remember yesterday, not tomorrow. Entropy goes up. Systems become more disordered over time. That's the second law of thermodynamics, and it seems to be the one rule that doesn't like running backward. Here's the puzzle. If the core laws allow time to move both ways, why does everything we observe go one way? Let's break it down. Start small. Imagine two particles in space. They move toward each other, bounce off, and go their separate ways. If you film that and play it in reverse, it still makes sense. The motion, the collision, the energy, all look normal. You can't tell which version is forward and which is backward. The math agrees. Now look at a more complex situation. A hot cup of coffee cools down as it sits on the table. Heat moves from the coffee to the air. This process seems to only go one way. You never see heat jump back into the coffee to make it hot again. But the atoms and molecules that make this happen, they still follow time-symmetric laws. So the asymmetry isn't in the laws. It's in how those laws play out in large numbers. That's what entropy describes. It's a measure of how many ways the parts of a system can be arranged. A neat stack of papers can be arranged in fewer ways than a messy pile. So the messy pile is more probable. Over time, systems tend to move toward more probable states. That's why disorder or entropy increases. But this explanation only pushes the problem back one step. Why did the universe start in a low entropy state to begin with? Why did it begin in such an ordered condition, making all this disorder possible over time? There's no easy answer. Some physicists suggest that the arrow of time, the forward direction we all feel, comes from that low entropy start. Others say the universe could be time-symmetric overall, and we're just in a section that happens to be going forward. That's where things get strange. Picture time as a long line stretching in both directions. Our universe could be sitting in the middle, with time flowing outwards in opposite directions. In one half, time flows the way we know it, entropy increasing, stars aging, people living and dying. In the other half, things might look reversed. From their point of view, we're the ones moving backward. This idea doesn't break the laws of physics. It matches the symmetry in the equations. It's just hard to think about because we're stuck experiencing only one side of it. Then there's quantum mechanics. That adds a new layer. In quantum theory, particles exist in a range of possible states until they're measured. Once you observe them, their state collapses into a single outcome. This collapse seems to pick a direction in time. Before the measurement, the system evolves smoothly, symmetrically. After the measurement, it snaps into place. That break feels one way. But there's a model called the two-state vector formalism. It says maybe we shouldn't think of particles as evolving only from past to future. Maybe they're guided by conditions at both ends, past and future. In that view, the full description of a quantum system includes a state coming from the past and another coming from the future. The present is shaped by both. To make that clearer, think of a simple example. A photon travels from point A to point B. Usually, we describe its path starting from A, using probabilities to predict what might happen at B. But the two-state approach says we should also consider a state coming from B back to A. Only when both states are combined do we get the full picture. This sounds odd, but again, it doesn't break the math. It's just a shift in perspective. There's another way to look at the paradox using something called the block universe. That's the idea that all of time, past, present, and future, exists at once, like a map. We move through it, but the whole thing is already there. In that case, time's direction is a feature of our experience, not a property of the universe itself. You could think of it like a movie reel. The story unfolds frame by frame, and it feels like it's moving. But the entire film already exists. Our brains experience it as flow, but the structure is fixed. Still, this doesn't explain why the flow goes one way and not the other. If all times exist equally, why do we only remember the past? Why don't we remember the future? That's where causality comes in. In our experience, causes come before effects. You turn the key, the engine starts. You flip a switch, the light turns on. But again, the equations allow it to go both ways. In theory, an effect could come first. We just don't see that happen. Some interpretations suggest this is a matter of information. Once a cause happens, its effects spread out. They're harder to reverse. The light from the bulb goes off in all directions. You can't gather it all back. That spread makes reversal unlikely, even if not impossible. Imagine spilling ink in a glass of water. You could, in theory, run the physics backward and get the ink back into the dropper. But in practice, too many tiny details get lost. The process is irreversible, not because the rules forbid it, but because the odds are too small. This practical asymmetry might be what gives us the arrow of time. Now layer on something even deeper, cosmology. The universe is expanding. That gives it a kind of direction. In the early moments after the Big Bang, things were dense, hot, and orderly. As the universe grows, it cools and spreads out. Complexity builds. Entropy increases. Maybe the expansion of the universe is tied to our sense of time flowing forward. If the universe started collapsing instead, maybe our arrow would point the other way. It's hard to test this. We only have access to one path, the one we're on. But ideas like the time symmetry paradox make us question how much of our experience is fundamental and how much is just perspective. We live in the forward-moving version of time, but the rules behind everything allow for both directions. The universe might not care which way the clock ticks, only we do. A particle should be a particle. A wave should be a wave. That's the way things work in the world we see. A baseball doesn't ripple through the air like a sound wave. Light doesn't bounce like a ball. Or at least, that's what we used to think. Wave-particle duality breaks that clean line. It shows up right at the core of quantum mechanics. It says something can be a wave and a particle at the same time. Not in a metaphorical way, not as a trick of language, but in how it actually behaves when you test it. It started with light. In the 1600s, Isaac Newton said light was made of particles. A few decades later, Christian Huygens said light was a wave. Both were great scientists. Both had evidence. They couldn't both be right, or so it seemed. Over the next few centuries, people ran more and more experiments. Some made light look like a wave, others made it look like particles. The double-slit experiment, first done with light in the early 1800s, showed an interference pattern. That's what you expect from waves. One wave from one slit meets another wave from the second slit. Where the peaks align, the light adds up. Where a peak and valley meet, they cancel out. You get a striped pattern on the screen behind. But by the early 1900s, things changed. Max Planck and Albert Einstein found that light also comes in discrete chunks, quanta. You can't divide light endlessly. Einstein used this idea to explain the photoelectric effect. You shine light on a metal plate, it spits out electrons, but it only happens if the light has enough energy. You can make the beam as bright as you want, but if the frequency is too low, nothing comes off. That suggests light is delivering packets of energy, particles, not waves. Those particles are called photons. So which is it? Is light a wave or a particle? Here's the strange part. It depends on how you look. If you run an experiment to test wave behavior, light behaves like a wave. If you set it up to test for particles, it behaves like particles. Not because you disturbed it or knocked it around. The setup alone seems to decide the outcome. And this isn't limited to light. In 1923, Louis de Broglie asked a bold question. If waves can act like particles, can particles act like waves? He proposed that electrons, tiny bits of matter, should also have wave-like properties. This wasn't just a guess. He used a formula to relate a particle's momentum to a wavelength. Then came the tests. In 1927, Clinton Davison and Lester Germer fired electrons at a crystal. Instead of bouncing off in all directions like particles hitting a wall, the electrons created an interference pattern. That only happens with waves. The experiment confirmed de Broglie's idea. Electrons, which have mass and charge and take up space, were behaving like waves. That's when people started to realize wave-particle duality wasn't a weird trait of light. It was part of the nature of all quantum objects. Imagine this in a different way. You fire a single electron through a pair of slits, one at a time. There's no chance it splits in half. It has to go through one slit or the other. But if you don't look, and you do this over and over, you still get an interference pattern on the screen. It builds up slowly, dot by dot, as if the electron interfered with itself. It acted like a wave going through both slits. But when you place detectors at the slits to find out which one it actually used, the interference vanishes. Now the electron behaves like a particle again. The only thing that changed was whether or not you tried to find which path it took. You might think it's just because of measurement that we disturbed the electron. But the same pattern appears even if you set up the whole system in a way that can't possibly affect the particle. The shift in behavior doesn't come from physical contact. It comes from what kind of question you ask. So the duality isn't about flipping from wave to particle and back again. It's about the quantum object being something more general, something that shows different sides of itself depending on how you test it. Like a coin spinning in the air that only shows heads or tails when you catch it. This idea reshaped how scientists think about particles. They don't move along neat paths like little marbles. Instead, their behavior is described by a wave function, a spread of probabilities. The wave function tells you where a particle is likely to be found, or how fast it might be going, or which direction it might take. But it doesn't give you a definite answer until you make a measurement. Take the classic example of a single photon. You shoot it at a mirror angled at 45 degrees. It can either bounce off or pass through, depending on the type of mirror. In quantum terms, until you detect it, the photon is in a state that includes both outcomes. It's not just undecided, it's genuinely in a superposition. Only when it hits a detector does it settle into one path. Wave-particle duality is built into that idea. The wave function spreads the particle out like a wave, but the detection snaps it into a particle-like result. Here's another example. Think of a laser pointer. It looks like a solid red dot, but the laser emits photons one by one. They're sent out in a straight line with the same phase and frequency. That's a wave property. The sharp dot comes from coherence, which means all the photons are in sync. But each detection, each little hit on a surface, is a single particle event. You only get the wave-like behavior when you look at many photons together. That shows how the particle and wave aspects aren't in conflict. They're two ways of describing the same thing at different scales. In a classroom, wave-particle duality is often taught with diagrams and analogies, but none of them quite capture the full weirdness. That's because we don't have anything like it in the world we live in. Everything we see is either solid or fluid, either thing or motion. But in the quantum world, things don't commit to being things until you interact with them. That doesn't mean reality is fuzzy or vague. The rules are exact. The equations give accurate predictions, but they don't match our expectations of how objects should behave. And wave-particle duality is one of the first cracks in that illusion. It tells us that the way we observe something can shape what we find. That matter and energy are not separate categories, but parts of a deeper structure. That light can interfere with itself, and that electrons, those building blocks of atoms, can do the same. And we didn't come to this idea through guesswork. It came through experiments, repeated, verified, often with results that surprised even the people running them. No matter how carefully we check, the same behavior shows up again and again. Electrons act like waves, photons hit like particles, and somewhere in between, quantum mechanics does its work. A particle can go through a wall. That sounds wrong, but in quantum mechanics, it's not only possible, it happens all the time. In everyday life, if something doesn't have enough energy to climb a hill or break through a barrier, it stops. A car won't roll over a wall unless it's going fast enough. A ball won't get out of a pit unless you throw it hard. That's how the world works at large scales. But at the atomic level, particles don't play by those rules. In quantum mechanics, there's something called a potential barrier. Think of it like a hill or a wall that a particle isn't supposed to cross unless it has enough energy. But here's the twist. Sometimes, even when the particle doesn't have enough energy, it shows up on the other side of the barrier. It acts like it passed through the wall instead of over it. This is called quantum tunneling. The math behind it says that particles aren't just in one spot. They exist as wave functions, spread out clouds of possibilities. These wave functions can stretch beyond barriers, even into areas the particle isn't likely to reach. And if the barrier is thin enough and the wave function stretches far enough, there's a chance, however small, that the particle will be detected on the other side. It's as if it tunneled through, even though it shouldn't have had the energy to do it. This isn't just theory. We see it in action. In fact, without tunneling, the sun wouldn't shine. Inside the sun, hydrogen atoms fuse to make helium. That fusion gives off energy. But here's the problem. Under classical physics, those hydrogen atoms don't have enough energy to get close enough to fuse. The positive charges in their nuclei repel each other. The barrier is just too strong, and yet fusion happens anyway. That's because quantum tunneling lets the protons get close enough for the strong nuclear force to take over. Without tunneling, stars wouldn't work. Take another example, radioactive decay. In some atoms, the nucleus is unstable. Particles inside it, like alpha particles, don't have enough energy to break out. The walls of the nucleus are too high, but again, they sometimes escape. That escape is tunneling. The particle exists as a wave inside the nucleus, and part of that wave leaks through the wall. Now and then, the particle shows up outside, and the atom decays. We use tunneling in technology too. The tunnel diode, invented in the 1950s, relies on this effect. So do scanning tunneling microscopes. These devices let us see atoms on surfaces. A sharp metal tip hovers just above the surface, with a small gap in between. When electrons tunnel across the gap, the current gives a signal. By measuring how the current changes, we can build a picture of the surface, down to the atomic level. But the oddities don't stop there. One strange aspect of tunneling is how fast it seems to happen. If you measure how long it takes a particle to tunnel through a barrier, you get a result that looks almost instantaneous. In some cases, it even seems like the particle travels faster than light. That's not supposed to happen. Nothing should go faster than light. But tunneling doesn't involve movement in the usual sense. The particle doesn't travel through the barrier in a straight line. It just appears on the other side. So it's not breaking the speed of light. It's sidestepping the rules entirely. Imagine a train trying to go through a mountain. Normally, it would need a tunnel. But now, picture a situation where the train disappears at the base of the mountain and reappears on the other side, as if the mountain wasn't there. It's not speeding. It's not even moving in the regular sense. That's tunneling. You might wonder why we don't see things like this at our scale. Why don't baseballs tunnel through bats? Why don't cars tunnel through each other on the road? The answer is probability. At the quantum level, tunneling has a small chance of happening, but as objects get bigger, their wave functions get tighter, and the odds drop fast. For a baseball to tunnel through a wall, you'd have to wait longer than the age of the universe. The effect is real, but the chance is so low, it might as well be zero. That's why it stays hidden in the microscopic world. Let's take a closer look at that wave function. It tells us where a particle is likely to be. Near the barrier, the wave function starts strong. Inside the barrier, it gets weaker, but it doesn't go to zero. That small part that leaks through is what makes tunneling possible. If the barrier is too thick or too high, the wave drops too low, and the chance of tunneling disappears. But if the barrier is thin enough, the wave survives, and the particle might show up on the far side. Now think about how strange this is. A particle doesn't just sit in one place, it spreads out, and its ability to get through a wall depends on how much of its wave function can stretch beyond that wall. It's not really going through the way we imagine. It's more like the particle was never in just one spot to begin with. That's hard to picture, but it fits with everything quantum mechanics tells us. There's also something called the energy-time uncertainty principle. It says that for very short periods, energy can be uncertain. In simple terms, the universe can borrow energy for a moment, as long as it pays it back quickly. This idea helps explain how tunneling works. A particle might not have enough energy to cross the barrier normally, but for a brief moment it can borrow just enough to slip through. That might sound like a loophole, but it's part of how the quantum world functions. These tiny borrowings are built into the math, and they match what we see in experiments. Tunneling also plays a role in modern electronics. Transistors, which power everything from phones to laptops, are getting smaller and smaller. At some point, the components get so tiny that electrons start to tunnel where they shouldn't. That leads to leaks in circuits. Engineers have to design around these effects to keep devices working. The challenge grows as devices shrink and tunneling becomes more common. One proposal for using tunneling is quantum computing. In some designs, tunneling can flip quantum bits from one state to another. This lets the system explore many paths at once, using the full range of quantum behavior. That's still a work in progress, but tunneling is a key part of what might make quantum computers powerful. There are still open questions. One is whether the tunneling particle knows about the barrier before it gets there. That sounds impossible, but some interpretations of quantum mechanics suggest that the entire setup, the particle, the barrier, the detector, are part of one whole system. In that view, the outcome is not just about the particle hitting a wall. It's about the full context of the experiment all at once. Even stranger, some researchers have looked at whether information can travel through barriers using tunneling. Could one particle sense the setup on the other side without ever entering it? Some results hint at odd behaviors that aren't easy to explain. But so far, nothing breaks the core rule that information can't move faster than light. Still, the questions keep coming. Tunneling shows that particles don't always follow the straight path. They don't always obey the rules we expect from the world we see. They can end up in places they shouldn't reach by means that don't quite make sense. And yet, the math holds. The measurements match. The effect is real. Quantum tunneling is one of those things that sounds like magic until you look closer. Then it sounds like physics, but not the kind we grew up with. This kind works in shadows. It works in probabilities. It allows particles to vanish from one side and reappear on the other. And even when you understand how it works, it still feels a little like cheating. What if something could be both alive and dead at the same time? Not in a poetic sense, but in a real, physical way. That's the question Erwin Schrödinger asked, and to show how strange quantum mechanics could be, he put a cat in a box. Not a real cat. Schrödinger never did the experiment. It was a thought experiment. an idea meant to show what happens when you take quantum rules and apply them to the real world. In the 1930s, quantum mechanics was still new. Physicists were figuring out how small particles like electrons and photons behave. These particles didn't act like everyday objects. Instead of being in one clear place or moving in one clear direction, they could exist in a state called superposition. That means they could be in several positions or states at once, at least until someone observed them. Once a measurement was made, the superposition would disappear. The particle would collapse into one definite state. Before that, it wasn't that the particle was hiding its real location. It genuinely didn't have a specific one. It existed in a blur of all possible outcomes. This idea was hard to swallow. It worked in equations and in labs, but it didn't make sense when applied to things we can see and touch. Schrödinger wanted to show just how absurd it would be if quantum behavior scaled up to the size of everyday objects. That's where the cat came in. Picture a sealed box. Inside the box is a cat. Also in the box is a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The setup works like this. If the atom decays, the Geiger counter detects it. That triggers the hammer, which breaks the vial, and the poison is released. The cat dies. If the atom doesn't decay, nothing happens. The cat stays alive. Radioactive decay is a quantum event. There's no way to predict exactly when the atom will decay. Instead, quantum mechanics says there's a chance it will decay and a chance it won't. It exists in a superposition, both decayed and not decayed, until someone checks. That's the key. Until you open the box and look, the atom is in both states at once. And because the atom controls the rest of the system, the entire setup becomes entangled. The cat's life depends on the atom's state. So if the atom is in a superposition, the cat is too. The result? The cat is both dead and alive at the same time. Not just unknown, not just hidden. According to the math, the cat is genuinely in a mixed state until you open the box and observe it. Only then does the system collapse into one outcome, dead or alive. This makes sense when you're talking about electrons. They're small and we can't see them directly. But when it comes to cats, the idea sounds ridiculous. Schrödinger knew that. That was his point. He didn't create the scenario to support quantum mechanics. He did it to show that something about the theory felt incomplete. The real puzzle is where the line is. When does a system stop behaving like a quantum object and start behaving like a classical one? Is it about size, complexity, interaction with the environment? Physicists started to look at a process called decoherence. In simple terms, decoherence is what happens when a quantum system gets disturbed by the outside world. Even a tiny amount of interaction, light bouncing off it, heat moving in, a random air molecule hitting it, can destroy the superposition. It becomes part of the larger world and starts acting like a regular object. You don't have to open the box. The box itself, or the air, or the walls might already cause the superposition to collapse. In practice, this means a real cat probably isn't ever in a superposition, even if you set up the experiment exactly as described. The system is too open, too connected to its environment. The quantum effects fade before you can measure them. But in theory, if you had perfect isolation, the math still says it's possible. To see how strange this really is, imagine a different version. Instead of a cat, think of a coin inside a box. You flip the coin, seal the box, and walk away. You don't know whether it landed heads or tails, but you assume it landed one way or the other. It's just hidden from you. But in quantum mechanics, the coin wouldn't have landed yet. It would be spinning in a mix of both heads and tails until you open the box. Only then would it settle into one outcome. That's the difference between uncertainty and superposition. In classical physics, things have definite states. We just don't always know them. In quantum physics, the state doesn't even exist until it's observed. Some physicists were fine with this. They accepted that quantum mechanics didn't match our everyday experience. They focused on the math, which worked and gave correct predictions. Others wanted a clearer picture. They proposed alternate interpretations. One famous one is the many worlds interpretation. It says that when a quantum event occurs, all possible outcomes happen, but in separate branches of the universe. In one world, the cat lives. In another, it dies. The universe splits and both outcomes are real, just in different versions of reality. That's a bold claim. It avoids the need for collapse. There's no need to explain when or how the superposition ends. It never ends, it just branches. But it raises its own questions. If the universe is constantly splitting, why don't we notice? Where are these other versions? Can we ever interact with them? Schrödinger's cat has become more than a physics example. It's used in conversations about AI, ethics, philosophy, even literature. But at its core, it's still about one thing: the strange line between what is and what isn't. In the lab, scientists now work with quantum systems that stay in superposition longer than ever before. They've built tiny circuits that can be in two energy states at once. They've cooled particles close to absolute zero to reduce outside noise. Some of these experiments start to stretch into what you might call the mesoscopic world. Not as small as an atom, not as big as a cat. Still quantum, still weird. Every time someone pushes that boundary, we get closer to answering Schrödinger's challenge. How far can superposition go? Can we ever see it in something we recognize? A grain of dust, a virus, a bacterium? The cat in the box is still just a thought. But the question it asks is real. What does it mean to say something exists? What changes when we look at it? And how much of the world is shaped not just by what happens, but by whether or not we decide to watch? You can know where it is, or you can know how fast it's going, but not both at the same time. That's the core of the uncertainty principle, and it doesn't come from faulty tools or sloppy measurements. It's built into the way the universe works. This isn't just a physics problem, it pulls at something deeper. It raises questions about control, prediction, and the idea that everything follows a fixed path. That idea, known as determinism, says that if you knew the position and speed of every particle, you could know the future completely. But the uncertainty principle says you can never know those things at the same time. And that one limit changes everything. To understand what's at stake, think about the old way of seeing the universe. Newton's laws gave people a sense that nature was like a machine. Every motion followed a rule. If you dropped an apple or fired a cannonball, you could write an equation to describe its path. If you had enough data and a big enough calculator, you could predict the future down to the smallest detail. Pierre-Simon Laplace, a French thinker, imagined an intelligence, later called Laplace's demon, that knew the position and motion of every atom. With that knowledge, the demon could see all of history and all of the future at once. That's determinism. It's clean. It's simple. But it doesn't match what we find at the smallest scale. In the early 20th century, quantum mechanics began to replace Newton's clockwork picture. It described a world where particles don't follow neat paths. Instead, they exist in a blur of possibilities. Werner Heisenberg put this into clear terms. He said that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. It's not a problem of instruments. It's not like using a blurry microscope or a shaky camera. The uncertainty is part of the particle itself. It's not hiding a real position and speed that we just can't see. The particle doesn't have both a fixed position and momentum at the same time. To see how this matters, imagine a small marble rolling across a table. In the world we live in, you can measure its speed and position without much trouble. You might make small errors, but the marble has a definite place and a clear path. But shrink the marble down to the size of an electron, and the rules shift. Now the act of measuring changes the system. If you shine light on the electron to see where it is, the light gives it a push, which changes its speed. If you try to measure its speed instead, you lose track of where it was. This isn't just a measurement issue, it's a fundamental limit. So what does this mean for determinism? If you can't know both position and momentum, then you can't predict the future with perfect accuracy. You can't even describe the present with total certainty. That breaks the idea of a fixed, knowable universe. In classical physics, if a ball rolls down a hill, you can say exactly where it will be at any point in time. In quantum physics, you can only talk about probabilities. You might say there's a 70% chance it'll be here, for all, and a 30% chance it'll be there. The equations of quantum mechanics don't tell you what will happen, they tell you what might happen. This is where many people feel a shift. They ask, is the universe just playing dice? Is reality based on chance, not certainty? Albert Einstein didn't like that. He famously said, God does not play dice with the universe. He believed that the randomness in quantum mechanics had to be a sign of something missing, some deeper layer we hadn't found yet. But decades of experiments have shown that the uncertainty is real. It's not just noise, it's not just ignorance, it's the way things are. One way to make this clearer is through a simple scenario. Think of a single atom emitting a photon of light. When will the photon be released? Quantum theory says it happens at random. You can't predict the exact time. You can only say how likely it is to happen over a certain period. That one moment, the release of a photon, might then trigger a chain of events in a detector, a sensor, or even a human eye. And yet, it starts from something that doesn't have a fixed time. That's not the kind of world a strict determinist would expect. Now let's connect this to something more practical. Modern computers rely on semiconductors, and those use quantum effects to control the flow of electrons. Engineers don't know where every electron is. They rely on probabilities. The devices work not because we know each detail, but because we understand the general behavior. That's the shift from certainty to statistical control. There's a similar shift in how we think about causation. In a deterministic system, cause and effect are tight and direct. But in a quantum system, you can have causes that lead to several possible outcomes. One cause, many paths. You don't get to pick the path. The system chooses one when it's measured or observed. The uncertainty principle doesn't just affect what we know, it affects what exists. Until a measurement happens, a particle doesn't have a definite state. Its properties are spread out in a wave of possibilities. When you observe it, that wave collapses, and you see one outcome. This collapse isn't like flipping a coin. With a coin, you assume it's heads or tails before you look. With a quantum system, it really isn't anything until the measurement. This puts pressure on the idea that everything is predetermined. If you can't know the future, and the future itself isn't fixed until you interact with it, then determinism as it was once imagined doesn't hold. The rules still follow logic. The math still works, but the outcomes are not written in stone. Even so, people look for ways to rescue determinism. One idea is hidden variables. Maybe the particle does have fixed properties, but we just don't know how to measure them yet. These variables would hide behind the uncertainty and make the world predictable again, if we could find them. But experiments testing hidden variable theories, like Bell's theorem, have shown that local hidden variables can't explain quantum behavior. The uncertainty remains, no matter how hard you look. That doesn't mean the universe is out of control. It means it runs on rules we're still learning how to think about. The uncertainty principle tells us that knowledge has limits, not because we aren't clever enough, but because the world is built that way. And that changes how we understand prediction, time, and the flow of cause and effect. You can copy a file, you can copy a photo, you can even copy someone's voice. But in the world of quantum mechanics, there's one thing you absolutely can't copy: a quantum state. That's not a limitation of our technology. It's a law of nature, and it's called the No-Cloning Theorem. This idea seems strange at first. We're used to living in a world where information can be duplicated. You can back up your hard drive, you can print out a document as many times as you want. But when you work with quantum information, the rules are different. In fact, they're strict. If you try to copy a quantum state, you'll fail. Not because you're doing something wrong, but because the universe doesn't allow it. A quantum state is the full description of a quantum system. Think of it as everything there is to know about a particle. That includes its position, momentum, spin, and more, all wrapped up in something called a wave function. But here's the catch: you can't see the wave function directly. You can only interact with it through measurement, and measurement changes it. To understand why copying is impossible, consider a thought experiment. Say you have a particle in an unknown quantum state. You don't know its exact state, but you want to make an identical copy of it. If quantum states behaved like classical data, that would be simple. You just read the information and duplicate it. But in quantum mechanics, reading the state changes it. Once you measure it, you collapse the wave function. The system picks one outcome, and the rest of the possibilities vanish. You've lost the original form of the state, and with it, the ability to make a true copy. In 1982, physicists Wouters and Zurek put this limitation into a formal proof. They showed that no process in quantum mechanics can take an unknown quantum state and produce an exact copy of it. The proof is mathematical, but the logic behind it is grounded in what measurement does to a quantum system. It breaks the system's full state down to one part of itself, and you can't recover the full original from that single part. Now imagine you're building a quantum computer. You want to store data in quantum bits, qubits. These qubits can hold much more information than classical bits because they exist in superposition, a blend of possible states. That's part of what makes quantum computing powerful. But it also introduces challenges. In a classical computer, if something goes wrong with a bit, you can make a backup copy and restore the data. But in a quantum system, you can't make a backup the same way. The No-Cloning Theorem blocks you from just copying your qubit and saving it somewhere else. So what do physicists do? They use quantum error correction codes. These codes don't rely on copying. Instead, they spread the information of a single qubit over multiple qubits in a special entangled state. If one part of the system gets disturbed, the structure of the code allows you to recover the original information without ever making a true copy. It's also worth thinking about how the no-cloning theorem protects certain aspects of quantum communication. Suppose someone wants to send a secret quantum message. If a third party tries to intercept it, they'd need to make a copy of the quantum state without disturbing it. But they can't. Any attempt to clone the message would either destroy it or alert the sender and receiver. That's why quantum key distribution, a method for secure communication, relies on this principle. The impossibility of cloning is what makes eavesdropping detectable. Let's break this down with a simple analogy. Imagine someone gives you a sealed envelope. Inside, there's a color written on a card, red, green, or blue. You're not allowed to open the envelope. Your job is to make a perfect replica of whatever's inside without ever looking. In the classical world, that's easy. You just peek, write down the color, and make a new card. But in the quantum world, peeking changes the color. You're not just finding out what it is, you're causing it to become something definite. Before you looked, the card could have been a mix of colors. After you look, it's only one. So whatever replica you make after peeking can only reflect that one piece of information. The rest is gone. There's a deeper implication here too. The no-cloning theorem tells us that quantum information can't be treated like classical information. It has structure, limits, and behavior that resists simplification. That's why quantum systems are both powerful and fragile. Their strength lies in superposition and entanglement, features that don't exist in our everyday world. But those features also mean you can't handle quantum information the way you handle files on your computer. Think about teleportation, not the sci-fi kind, but quantum teleportation. It's a process that allows you to send a quantum state from one place to another. The no-cloning theorem plays a key role here. To move the state, you first destroy it at the source. Then, you recreate it at the destination using shared entanglement and classical communication. The state never exists in two places at once. You're not copying it, you're transferring it. The original is gone before the new one arrives. If cloning were allowed, teleportation wouldn't be necessary. You just copy the state and send the clone. But you can't, so teleportation becomes the next best option. This also affects how we think about knowledge. In classical terms, knowledge is something you can duplicate, pass around, and store in multiple places. In the quantum world, knowledge is more elusive. It's tied to a system in a way that resists duplication. That changes how we think about certainty. You can't always know a quantum state in the way you'd like to. You can prepare it, interact with it, and even control it in some ways. But you can't fully capture it without losing it. Try to imagine someone giving you a key made of light. Not just any light, but a photon in a precise quantum state. If you could clone it, you could make endless copies of the key. But because of the no-cloning theorem, you can't. If you try, the photon's state will change. You'll end up with something different, something that no longer opens the lock. This isn't a bug in quantum mechanics. It's a feature. It keeps the system honest, it limits what you can know, and it keeps your actions tied to consequences. You can't peek without changing what you see. You can't copy without destroying the original. And you can't cheat the rules because the rules are baked into the structure of reality itself. Even now, scientists and engineers have to design around this limitation. They don't try to beat it, they accept it and find ways to work with it. In that way, the No-Cloning Theorem does more than set boundaries. It shapes what's possible. It defines the edge between classical and quantum and forces us to think carefully about what it means to hold, send, and protect information in a world that plays by quantum rules. What if nothing exists the way you think it does until something looks at it? That idea isn't philosophical fluff. It's a real question raised by quantum mechanics. In fact, it's at the center of how reality seems to work at the smallest level. In everyday life, we assume things are there whether or not we're looking. A tree stands in the forest whether someone walks by or not. A rock lies on the ground whether it's seen or touched. But that assumption breaks down when we zoom in to the scale of atoms and particles. In that world, things behave differently. And according to many experiments, particles don't settle into a single state until they're measured. That idea comes from the basic principles of quantum theory. At the heart of it is something called the wave function. A wave function is a mathematical object that holds all the possible states a particle could be in. For example, it could describe an electron that might be in multiple locations, spinning in several directions or moving at different speeds, all at once. The wave function doesn't pick one of these possibilities. It keeps them all open. When a particle hasn't been observed, its wave function remains spread out. It's not in one place, it's in many. It doesn't have one path, it has all of them. Only when someone measures it does the wave function collapse, and the particle lands on a single outcome. That's what the math shows, and that's what the experiments suggest. One of the clearest examples of this is the double-slit experiment. When electrons, or even larger molecules, are fired toward two slits with no measurement tools watching which slit they go through, they act like waves. They seem to interfere with themselves, like ripples on water. The result is an interference pattern on a screen behind the slits with bright and dark bands showing where the waves added up or canceled out. But when scientists set up a detector to find out which slit each particle went through, the interference vanishes. The electrons hit the screen in two clear bands, like particles going through one slit or the other. The act of measuring changes the outcome. But more than that, it raises a question. What was the electron doing before we measured it? Did it really go through both slits at once? Or was it in some in-between state that we don't fully understand? This isn't just a strange lab trick. It's built into the structure of quantum mechanics. In this framework, a particle doesn't have properties like position or momentum until we measure them. That's not because we lack the tools to find out. It's because before measurement, those properties don't exist in a definite way. That's where things start to get uncomfortable. If an electron doesn't have a position until we look, what does that mean for objects made of electrons? What does that mean for matter in general? Are things only real when we observe them? Physicist Eugene Wigner once suggested that consciousness might play a role in collapsing the wave function. In his view, the universe might not settle on a definite state until a conscious observer looks at it. That's a bold idea, and not one that many scientists accept today. But it shows how far-reaching the implications can be when we ask whether unobserved things exist in any definite way. To get a better grip on the idea, imagine a small box. Inside the box is a single particle. You close the box and seal it shut. As far as quantum mechanics is concerned, that particle has no fixed location while the box stays closed. It doesn't sit in one corner. It doesn't hover in the middle. It exists in a range of possible places at once, all described by its wave function. Now imagine you open the box and measure the particle's location. At that moment, the wave function collapses. The particle appears in one spot and you write it down. But before you looked, the idea that it was in a single place doesn't make sense in quantum terms. It wasn't hiding from you. It wasn't waiting. It simply didn't have a defined position at all. Some might say that this is just about what we know, not about what the particle actually is. But quantum theory doesn't support that view. The wave function isn't just a placeholder for ignorance. It's the best tool we have for describing how particles behave. And it tells us clearly that particles don't settle into a state until they're observed. This plays out not just in lab experiments, but in real technologies. Quantum computers, for instance, depend on particles that can exist in multiple states at once, what's called superposition. These particles perform calculations by exploring many paths at the same time. But the moment we read the result, the system collapses into one final answer. That's observation at work. And without that final measurement, we can't make use of the outcome. Another example is quantum cryptography, which uses the behavior of photons to ensure secure communication. If someone tries to intercept the message and measure the photons, their act of observation changes the system. It leaves a trace. And that trace tells the intended receiver that the message was tampered with. Again, the reality of the system depends on whether or not it's observed. All this leads to a strange picture. In the quantum world, observation doesn't just show us what's happening, it helps create what's happening. It defines what can be said about a system. Without observation, the world stays in a state of uncertainty, a set of probabilities, not actual facts. Some interpretations try to avoid this conclusion. The many worlds interpretation, for example, says that all possible outcomes happen, each in its own universe. In that view, when you measure a particle, you don't collapse its wave function. Instead, the universe splits. One version of you sees the particle go left, another version sees it go right. But this leads to its own questions. Where are these other versions? Can they interact? What do we mean by a universe? Another view, called objective collapse theory, says that wave functions do collapse, but not just when we look. Instead, they collapse on their own after a certain time or under certain conditions. That would bring back an observer-independent reality. But no one has proved this yet. In the end, the simplest reading of the experiments we have is that reality depends on observation. Things like position, momentum, spin, and even time do not become definite until they are measured. And without measurement, these properties remain undefined. It's not that the particle is playing tricks. It's not hiding in some dark corner of the box. It's that the particle doesn't exist in a fixed state at all until something interacts with it in the right way. This doesn't mean the universe disappears when no one's watching, but it does mean that, at the smallest level, the act of observation plays a central role in shaping what we call real. It's not a passive process, it's part of how the system works. That's the picture quantum mechanics gives us, and as strange as it sounds, it matches the data. There's a kind of nothingness that isn't empty. That sounds like a contradiction, but it's one of the stranger truths at the heart of quantum physics. When most people think of a vacuum, they picture an absolute void, a place with no matter, no light, no air, no sound. In everyday life, that makes sense. A vacuum cleaner works by removing air. Space, far from planets and stars, is close to a vacuum. But in quantum field theory, even the deepest vacuum is not really empty. It's full of activity, just not the kind we can usually see. The idea starts with what's called the uncertainty principle. In simple terms, it says that certain things in physics can't both be known exactly at the same time. One of those pairs is energy and time. If you look at a very short moment in time, energy can become fuzzy. It doesn't have to hold still. And for brief periods, this lets the vacuum cheat. It borrows energy and uses it to make particles that shouldn't be there. These are called virtual particles. They're not fake, but they don't stick around long enough to become real particles. They pop in and out of existence so quickly that we can't measure them directly, but we can see their effects. A good example is something called the Casimir effect. Picture two metal plates in a vacuum, placed very close together. There's no light between them, no air, no heat. You'd expect that nothing would happen. But over time, those plates actually move. They're pushed together, not by any force you can see, but by the vacuum itself. The reason comes from virtual particles. These particles can appear anywhere in the vacuum, but the space between the plates limits the kinds of particles that can exist there. Outside the plates, the vacuum has more freedom. There are more possible states for the virtual particles to take. So the pressure from the outside vacuum becomes slightly greater than the pressure inside. That tiny imbalance pushes the plates together. This shows that the vacuum isn't empty. It has energy, even though there's no visible source for it. This energy is called vacuum energy, and it's one of the strangest ideas in physics. It says that nothingness, when examined closely, becomes something. A quiet space still hums with potential. Now, if this energy is everywhere, you'd think it should have a big effect on the universe. It turns out it does. In fact, vacuum energy plays a role in how the universe expands. When physicists look at distant galaxies, they see that the universe isn't just expanding, it's expanding faster and faster. Something is pushing space apart. That push is often called dark energy, and one idea is that dark energy might be the large-scale effect of vacuum energy. But there's a problem. When physicists calculate how much vacuum energy there should be, the numbers get extreme. The math says there should be a huge amount of energy packed into every bit of empty space. But the actual effect we observe is much smaller, off by a factor of about 10 to the power of 120. That's a 1 followed by 120 zeros. It's one of the biggest mismatches between theory and observation in science. So something about our understanding must be missing. Either the math is wrong, or the way we think about the vacuum needs to change. But the basic idea that space itself holds energy is not in question. It shows up in the math, in the lab, and in the sky. Another place where virtual particles show up is around black holes. There's an idea called Hawking radiation, named after physicist Stephen Hawking. He proposed that virtual particles near the edge of a black hole could become real. Usually, a pair of virtual particles appears, then cancels out and disappears. But if this happens near the event horizon, the point beyond which nothing can escape, a strange thing can occur. One particle falls in, the other escapes. The escaping one becomes real. It carries away a small amount of the black hole's energy. Over time, this effect would cause the black hole to shrink. That's a bold prediction, and no one has observed Hawking radiation directly. But it fits with what we know about quantum fields and gravity. It also shows how virtual particles, though short-lived, can leave lasting marks. These particles also help explain something called the Lamb shift, a tiny change in the energy levels of hydrogen atoms. In a hydrogen atom, the electron orbits the nucleus in specific energy levels, but experiments show a small shift in those levels, just enough to notice, and more than the basic theory predicts. The explanation involves virtual particles. The vacuum around the atom isn't quiet. It creates fluctuations that slightly disturb the electron, nudging its energy. Even something as solid as a proton owes part of its mass to virtual particles. Inside protons and neutrons, you find quarks. These are held together by gluons, which are force carriers. But the space inside a proton is more than just quarks and gluons. It's a roiling mess of virtual particles that pop in and out, affecting the mass and structure of the whole thing. So when we say a proton has mass, that mass doesn't just come from the quarks. It comes from the fields that surround them and the particles that flash into existence for just an instant, then vanish. This tells us that even the things we think of as solid and unchanging are built on a shifting base. All of this points back to one idea. The vacuum isn't empty. It's not just a backdrop for action. It's part of the action. It has structure, energy, and influence. You might not notice it in daily life. You don't feel pressure from virtual particles when you walk through a room. But they're always there, shaping the rules that everything else has to follow. Virtual particles are not science fiction. They are a necessary part of the equations that describe how particles interact. In quantum electrodynamics, for example, the most accurate theory we have, virtual particles play a central role. They mediate forces, shift energy levels, and help explain why particles behave the way they do. They can't be isolated. They don't show up on a detector, but their fingerprints are everywhere. So we're left with a picture of the universe that doesn't rest on a hard, silent foundation. Instead, it sits on something alive with possibility. The vacuum is not an absence. It is a sea of potential, flickering with activity at every point. And what looks like nothing turns out to be full of influence and structure we're only beginning to understand. At the smallest scale we can imagine, space itself may not be smooth. It might not even be continuous. Instead, it may bubble and shift like the surface of boiling water. This idea is called quantum foam. It's not a metaphor. It's a serious idea in theoretical physics, first proposed by John Wheeler, the same physicist behind the delayed choice experiment. To understand quantum foam, you first have to zoom way in, way beyond atoms, beyond quarks. You go all the way down to the Planck scale, the level where space and time break down, where distance is about 10 minus 3 5/10 square minus 35 meters. That's a length so small we can't get close to testing it directly. But theories suggest something important happens there. At that tiny scale, space might not be calm or empty. Instead, it might fluctuate violently. It could shift in shape and energy so fast and so often that it looks like foam. The term makes sense when you imagine that, like bubbles in sea foam, little pockets of space could expand and collapse constantly. The reason for these fluctuations is rooted in quantum uncertainty. You can't know both the energy and the duration of an event exactly. So in a short enough time, enough energy can appear to form what are called virtual particles. These aren't real in the way we think of particles like electrons or protons. They don't last, but they affect the way real particles behave. They blink in and out of existence everywhere, all the time. Now take that idea further. If energy and particles can fluctuate, why not space itself? At the Planck level, spacetime might not be a smooth surface. Instead, it could be full of distortions, tiny wormholes, or bubbles that last for fractions of a second. These changes are too quick and too small for us to detect directly, but they might leave traces. That's where the anomalies come in. Some physicists think that quantum foam could show up as slight variations in the speed of light. Light travels fast, but if space isn't smooth, that speed could be slightly affected depending on the energy of the photon. Higher energy photons might hit more bumps in the foam. Lower energy photons might glide through more easily. This idea leads to a test. You look at light from very far away, like from a gamma ray burst billions of light years out. These bursts send out photons of many different energies at once. If all the photons travel through smooth space, they should arrive at the same time. But if space is foamy, higher energy photons could arrive slightly later. That delay would be tiny, but over billions of years, it could add up to something we can detect. Some telescopes have tried to look for this. So far, the results are mixed. A few measurements showed tiny delays that match what you'd expect if quantum foam is real. Others showed no delay at all. That's part of the problem. The effects are so small and the distance is so great that it's hard to be sure. Plus, gamma ray bursts themselves are chaotic, and it's hard to know whether the photons really left at the same time. Still, it's one of the few ways we might glimpse quantum foam directly. Another way might be through gravitational wave detectors. These are the instruments that picked up ripples in spacetime from black hole collisions. But those detectors are so sensitive that if space at small scales had irregularities, they might show up as noise, an unexplained jitter in the signal. Some researchers have even studied the leftover hum in the detectors when no known waves are coming through. They're looking for patterns that don't come from space events, but maybe from space itself. Let's build a scenario to make it easier to picture. Imagine you're walking across what looks like a polished floor. From far away, it seems smooth. But if you get down on your hands and knees with a magnifying glass, you start to see scratches, dents, tiny hills and valleys. Now imagine that floor isn't solid at all. Instead, it's boiling. At any given moment, little pieces of it rise up and fall back down. Some spots twist or shift in shape. You couldn't walk across it without feeling something. That's what it might be like for a photon moving through quantum foam. But photons don't have legs. They don't feel in the way we do. Instead, any changes in the foam would show up in their timing, direction, or energy. That's what scientists are trying to detect. They're not looking at the floor. They're watching the footsteps, trying to guess what the floor is made of based on how those steps change. Now here's where the anomalies become more than just curiosity. If we can find signs of quantum foam, we could start to test ideas in quantum gravity, where general relativity and quantum mechanics meet. Right now, those two theories don't play well together. Relativity describes gravity and the large-scale structure of space. Quantum mechanics describes particles and the very small. But at the Planck scale, they must come together. That's where foam lives. So any sign of foam is also a signpost on the road to a quantum theory of gravity. Some models even go further. They suggest that space could have a kind of texture, almost like a lattice or grid, where the foam is not random but patterned in some hidden way. If that's true, the effects on particles could be more predictable. That opens the door to new tests, possibly even experiments on Earth with ultra-precise lasers or clocks. There's also speculation about whether quantum foam could explain dark energy or dark matter. These are two of the biggest mysteries in cosmology. We see their effects, but we don't know what causes them. Foam might have enough energy in total to push space apart, or it might interact with matter in ways we haven't yet noticed. But these are just ideas for now. What we know is this: the vacuum of space is not empty. It's full of activity, even if we can't see it. Quantum field theory tells us that every point in space is a potential site of action. Even when nothing is there, fields exist, and they fluctuate. That's where the foam comes from, not from some separate thing, but from the fabric of space itself under the influence of quantum laws. Some people are uncomfortable with that idea. They want space to be clean and empty when nothing occupies it. But the math, and some of the data, says otherwise. It says space is alive with change, even when it seems still. And every so often, a signal comes in that doesn't quite match what we expect. It's small, it's quiet, but it hints at something deeper. Those are the anomalies. Not errors, not noise, but hints. Clues that point to a structure we don't yet understand, and possibly a path to something beyond the theories we have now. Imagine you flip a coin in New York, and at the exact same time, someone else flips a coin in Tokyo. You check yours. It's heads. And somehow, without delay, the other coin in Tokyo turns up tails, every single time. No message was sent. No signal passed between them. Yet they always match in a way that seems planned. That's not a magic trick. That's non-locality. Non-local reality is one of the strangest parts of quantum mechanics. It challenges the idea that things have to be connected by space and time to affect each other. It says that two particles, once linked in the right way, can remain connected no matter how far apart they are. Change one, and the other responds instantly. Not fast, instant. Not through space, but outside of it. This idea sounds wrong to anyone raised on classical physics, where nothing travels faster than light and cause must come before effect. But experiments keep showing that non-locality is real. The concept starts with something called quantum entanglement. When two particles are entangled, they share a quantum state. You can think of them as being part of the same equation. Change something about one particle, and the other one changes too, even if it's on the other side of the universe. Entanglement doesn't care about distance. The most famous case of this comes from the EPR paradox, named after Einstein, Podolsky, and Rosen. They thought quantum mechanics must be incomplete. In their view, the weirdness of entanglement meant the theory was missing something, some hidden variables that would explain what was really going on. Einstein famously called entanglement spooky action at a distance. He didn't like the idea that two things could affect each other without something traveling between them. To test this, physicist John Bell came up with a way to check whether these hidden variables could exist. He created a mathematical inequality, now called Bell's inequality, that described the maximum level of correlation you should see if particles were only influenced by local factors. Then, in the 1980s, physicist Alain Aspect ran an experiment that tested this inequality. His results broke it. Repeatedly. In the experiments, scientists created pairs of entangled photons and sent them in opposite directions. They then measured their properties, like polarization, at random angles. If hidden variables were responsible, the measurements would line up within certain limits. But that's not what happened. The results showed correlations that went beyond what any local theory could explain. The results pointed to a hard fact. The particles weren't behaving as if they had fixed properties from the start. Instead, they only took on definite states when measured. And the way they did that showed a kind of coordination that couldn't be explained by any signal traveling between them. Not unless that signal moved faster than light. And even then, it wouldn't be fast enough. The choice of measurement here affected the outcome there, with no time in between. So what does that mean? For one, it tells us that reality isn't built out of separate pieces that behave independently. When particles are entangled, they become part of one system, even if that system stretches across galaxies. Measuring one part is the same as touching the whole. Space, in a sense, stops being the limit. Let's break it down with a simple thought experiment. Imagine you have a pair of gloves, one left-handed, one right-handed. You place each one in a sealed box. You ship one box to the moon and keep the other on Earth. When you open your box and see the left glove, you instantly know the other box contains the right glove. But that's not spooky. The gloves had those properties from the start. There's no mystery. Now take a pair of entangled particles. You measure one and find it has spin up. The other, no matter how far away, will be spin down. But here's the catch. Before you measured either one, they didn't have a definite spin. The spin wasn't just unknown. It didn't exist in a set state. Your act of measuring created the result. And somehow, the other particle got the message instantly. Not because it was hiding something, but because it was never separate in the first place. This breaks with classical thinking. In the everyday world, objects have properties, and those properties don't depend on whether you look at them. A chair is in the room, whether or not anyone is watching. But in quantum mechanics, some things aren't settled until you measure them. And when you measure one entangled particle, the universe locks in the state of the other. There's another layer to this. You might think, okay, fine, they influence each other, but can we use that to send a message? The answer is no. Despite the instant link, quantum entanglement can't be used to transmit information in any practical way. You can't control the outcome of the measurement, so you can't use it to send a signal. The correlation is perfect, but the results are random. Still, the effect is real. We know it because it's been tested again and again, not just in labs, but in larger and larger setups. In 2017, Chinese scientists used a satellite to send entangled photons across 200 kilometers. The results showed the same correlations, the same non-local link, even at that massive distance. Space didn't break the connection, and the time it would take any signal to cross that gap was too long to explain the results. Some physicists have tried to get around this by suggesting there's a deeper reality behind the scenes, something we don't see, some kind of structure or network that links things instantly. Others say we need to give up our idea of space and time as fixed things. In quantum theory, the rules are different. Particles don't have locations in the way we think. Events don't always follow a clean order. One way to make sense of this is to stop thinking of particles as little objects flying through space. Instead, they're events. A particle isn't here or there. It's something that happens, something that becomes real when measured. And what happens in one place may be tied directly to what happens somewhere else, not through space, but as part of the same unfolding. That's what nonlocal reality points to. It's not about breaking the speed of light. It's about breaking the idea that distance limits interaction. At the quantum level, the universe doesn't always care about space. It cares about connection. Once two things are entangled, they remain part of the same thing, no matter how far apart they seem. Even if we can't use this to send messages, it still reshapes how we understand reality. It forces us to accept that the world doesn't run on simple local cause and effect. It runs on deeper rules, ones that we're only beginning to see.